Go ahead. Thank you very much.
Yes, so thank you very much for the invitation to this very interesting workshop. So I'm Phil Kunst, and I'm going to talk to you about topology and non-Hermitian systems. And more specifically, I'm going to tell you about exceptional points, symmetries, and the breakdown of the bulk boundary correspondence. And this is actually already illustrated in this figure here, where you see a spectrum of a Chern insulating model, where the system with open boundary conditions, the spectrum is shown in blue, with the red state being the chiral edge state. And if you now take the system under parallel boundary conditions, you see the spectrum for that shown in gray, and you see they're vastly different. And this is already a very strong indication that the bulk boundary correspondence is broken. So the aim of the talk is the following. So I want to study topology in the context of non-Hermitian systems, and you may wonder, why do you want to look at non-Hermitian systems? So let me briefly illustrate to you why they are actually relevant. And when I say non-Hermitian systems, I'm really going to focus on non-Hermitian Hamiltonians. And these non-Hermitian Hamiltonians find applications in classical systems, such as in mechanical systems, electrical systems, and also in optical metamaterials. And the relation here can really be made on the level of equations. So for example, for electrical systems, the admittance is related to your Hamiltonian. These non-Hermitian Hamiltonians are also relevant for quantum systems. So for example, if you think of a coupling to a weak Markovian bath, in this case, if you ignore, this is described by the Limplap-Master equation. And if you ignore the quantum jump terms, you actually see that your dynamics is governed by an effective non-Hermitian Hamiltonian. Another place where they would, for example, appear would be if you look at material junctions in quantum transport, where you then have a self-energy that is non-Hermitian. And if you're interested to learn more about this field of non-Hermitian topological phases, or I should say phenomena, then I would like to point you to a recent review paper that we published. So let's see, what are we going to do? So I mentioned to you losses, or I did not mention, but losses are very ubiquitous. And the question is, what are the consequences of such losses for topological phases? So first, we're going to look at exceptional points. These are degeneracies that appear in non-Hermitian systems. And then we're going to move on and talk about the breakdown of the bulk boundary correspondence in more detail. Okay, exceptional points. What are they? They are degeneracies in the spectrum at which the geometric multiplicity is smaller than the algebraic multiplicity. That means that the number of eigenvectors becomes incomplete, and your Hamiltonian is said to be defective at these points. So the very easy and simplest example one can think of is really this Jordan block you see here. This has two eigenvalues 0 and the eigenvectors coalesce. So there's only one right eigenvector like this and one left eigenvector like this. And also note that they are inequivalent to each other. So when do these exceptional points appear? So let's take a step back and look at what happens in Hermitian systems. For two bands to cross in a Hermitian system, you need to tune 3 parameters. And this you can easily see from this equation. So the cleanest way to write a 2x2 model is in terms of the polymatrices. So this is just a vector D that goes with the polymatrices. And here I have set the identity term to 0 because it's not relevant for the to study when the degeneracies appear. So for the degeneracy to appear, the eigenvalues, so these are the eigenvalues of this Hamiltonian, need to be equal to each other, which means that these terms under the square root need to disappear. And therefore, you need to set 3 equations to 0, which means you need to tune 3 parameters. And the most well-known example of this would be a while cone. Now, for non-Hermitian systems, it's actually a little bit different. Here, it turns out you only need to tune 2 parameters. So let's see how that works. Again, for a 2x2 system, you can write this equation, but now it's non-Hermitian, which means that this D vector has a real part and an imaginary part. So if you now write down the eigenvalues, you actually find this. This means that to find a degeneracy, you only need to solve 2 equations, namely the magnitude of this dr vector and these di vectors. These magnitudes need to be equal to each other, and these dr and di vectors need to be orthogonal to each other. So you only need to solve 2 equations, and therefore these exceptional points appear already generically in 2 dimensions. And are much more abundant in non-Hermitian systems than these ordinary degeneracies are. So let's look at some interesting properties associated with these exceptional points. So first of all, they are connected via Fermi arcs. So let's see how that works. I just told you exceptional points appear when two equations are satisfied. First, you want an orthogonality condition to be 0, and you want the magnitudes to be 0. So these two equations can be solved on some two-dimensional curve in some parameter space. So on this curve, you solve the dot product, whereas on this curve, the magnitude condition is satisfied, such that when these two curves overlap, you find your two exceptional points. So first of all, they appear in pairs, but if you think a little bit further, they're actually connected via Fermi arc. So say we're on this curve where the this dot product is satisfied, and you're in this region where the difference between the magnitudes is negative. You can, if you remember from the previous slide, on this particular curve, then you find that the real part of the energy disappears. So in the real part of the spectrum, you would find a Fermi arc connecting these two exceptional points. And you can make the same argument for the imaginary part of your spectrum, where you also find such an I Fermi arc. And such Fermi arcs have actually also been seen in experiment. So this is an example of a photonic crystal, a two-dimensional system where they have losses. And indeed, you see in the spectrum here, this is the experiment, this is the simulation, that these arcs appear. And this is really a non-Hermitian phenomenon in the sense that they appear in the bulk spectrum of your system, not on the surfaces like they do for the wild semi-metal. Another interesting property is that these exceptional points are non-analytical, which means that their energy eigenvalues, instead of going linearly with k like we know for wild cones, they actually scale with the square root of k. So the question now is, what happens if you add symmetries? So from the Hermitian case, we know that there are 10 symmetry classes available to us, written down by Adland and Sirnbauer. Now, it turns out that for non-Hermitian systems, there are 38 symmetry classes available. And this is because your transpose and your complex conjugation of your Hamiltonian are no longer equal to each other, which means that you now have two flavors of time reversal symmetry and particle hole symmetry. And there's also an additional symmetry. And this is the Pseudo-Hermitian symmetry defined this way. And this symmetry relates your Hamiltonian to its adjoint. So if we go back and again look at our two-band model that we already saw in the previous slide, let's see what the symmetry, what kind of consequences it has. And now I've reinstated the identity term for generality's sake. So there are basically two choices you can make for Q. You can either choose identity, but then your system becomes Hermitian, and that's not what we want. So we're going to choose instead one of the polymatrices, so say sigma x. Then if you plug in the symmetry here, or this term here with the Q sigma x, then you find that the x component of this d vector, as well as this d naught component, have to be real, whereas the y and z components of this d vector have to be imaginary. In other words, the dot product of the real and imaginary part of this d vector is automatically satisfied to be 0, and you only have the following equation left for your energy eigenvalues. Therefore, to find an exceptional point in the presence of the symmetry, you only need to tune one parameter, which means that an exceptional point is generic already in one-dimensional systems, which is why they also appear in parity time symmetric systems, if you're familiar with those. But you can also generically find, for example, exceptional lines or rings in two-dimensional systems, as illustrated in this example here. Okay, so let's move on to the second part of what I want to talk about, and this is a bit of a longer story. So I want to talk to you about the breaking of the bulk boundary correspondence. So what is this bulk boundary correspondence? It's a guiding principle for Hermitian topological phases, and it has two key properties. The first is that the spectrum under open boundary condition equals the spectrum under periodic boundary conditions plus the boundary spectrum. Moreover, you can define topological invariants, which then predict the number of boundary states. So you have a correspondence between the topological invariants, which you compute with your Bloch Hamiltonians, and it tells you what happens under open boundary conditions. I briefly want to mention to you an alternative approach to diagnose such topological phases, because we're going to use this to understand the non-Hermitian topological phases. And we're going to consider open boundary conditions from the start for this, and we're going to look at the SSH chain under open boundary conditions, and this is what that looks like. So just to remind you, the SSH chain has two sites in the unit cell, where the hopping inside the unit cell is T1 and between unit cells is T2. Then we're going to look for eigenstates of the following form. And these red and blue circles represent the sublattices of the SSH chain. And what I write inside is the amplitude of the wave function or the eigenstate that we're looking for. So this is a very pictorial way of writing what I'm going to look for, but actually this is the ansatz. So this is the wave function. This is the ansatz we're going to make, where this is the normalization. Here you have R, which appears here, and you see that it scales with the unit cell. So this M is the unit cell. So every time you go to the next unit cell, you pick up an extra factor of R, and it only has a non-zero weight on these red A sublattice sites. Then by making use of local destructive interference on the B's, on the blue sides, you actually can find an exact solution for this R. In this very simple way, say that we only have 3 sites in the system, then you apply your Hamiltonian to this wave function or to this eigenstate, and you see that you need to satisfy this equation. And this then gives you a result for R, which is simply the ratio of T1 over T2 of the hoppings inside the system with a minus sign. And it turns out that this ansatz is an exact solution in the systems with a broken unit cell, and it's an approximate solution in a chain with an unbroken unit cell, by which I mean you start with sublattice A and you end with sublattice B, as long as this ratio is smaller than 1, as long as this state is very well localized on the left in that case, and it does not feel the other end. And I just want to mention that these types of solutions are actually much more common. So here I wrote it for the SSH chain, but you can actually also find them for many more systems. They can describe all sorts of different types of topological states. And this is what we studied in these papers, but that's just a small aside. So how then can you use this to diagnose your topological phase? So just to remind you, this is your eigenstate, so the exact solution that we have. You see that there are 2 end modes when this ratio is smaller than 1. So I told you it exists when this ratio is smaller than 1 in a system with an unbroken unit cell. That means that you can write a similar solution that is on the B sides on the other hand. So you find 2 end modes as long as this ratio is smaller than 1. And that's indeed what you see in the energy spectrum. So this is the spectrum of the system under open boundary conditions. Blue are the bulk bands, red are the zero energy end states. And here you indeed see that where this ratio is smaller than 1, that you have these 2 zero energy end states in the gap of your system. There are no end states when this ratio is larger than 1, and the end modes gap out up to finite size effects in the systems when T1 over T2 is 1. And this we're going to use later to understand the non-Hermitian topological phases. And this also makes a lot of sense, because if this ratio is 1, then you see that this eigenstate is equally localized in each of your unit cells, and it has to be a bulk state. Therefore, it has to attach to your bulk bands. Okay, so let's now jump to non-Hermitian systems. So what about the non-Hermitian system? So now we're going to study a non-Hermitian version of the SSH chain. So again, you have 2 sites in the unit cell, A and B, in red and blue. And you see that inside the unit cell, I've now changed the hopping such that if you hop to the right, you have a hopping T1 minus gamma, and if you hop to the left, you have a hopping T1 plus gamma. And between unit cells, you have a hopping T2. The system has been experimentally realized actually in several setups, and I will show you these a little bit later in the talk also. So this system is extremely sensitive to boundary conditions, and such a sensitivity to boundary conditions of certain non-Hermitian systems was first realized in this PRL. And indeed, if you look at the spectrum of the system, again, here I've shown in gray the spectrum under periodic boundary conditions, in blue the spectrum under open boundary conditions, with red being the end states. You see that this is vastly different, and the gap closings actually appear for different parameter values. Moreover, if you look at the behavior of the bulk states, you see that they pile up at the edges. So you have, if you look at how the right eigenstates behave, you see they, in this case, they live on the left side of your system. That has to do with the choice of parameters, whereas the left eigenstates associated to the same eigenvalue are localized on the other end. And this is known as the non-Hermitian skin effect, and this term was first coined in this paper. However, if you look at the bar orthogonal product of the two, which means that I look at how left and right together, the left eigenstate and right eigenstate together, how they localize, you actually see that you have bulk band behavior. So when does this happen? Because I already alluded to the fact that this breaking of the bulk boundary correspondence does not happen for all non-Hermitian systems. So when does it happen? In And for that, we need to take one step back and look at the types of gaps, energy gaps that you can have in non-Hermitian systems. And from Hermitian systems, we note very simply, you can just have a gap like this, where you do not have an imaginary energy. So your system is gapped if there is a point that you can find a Fermi energy between your bulk bands. For non-Hermitian systems, you actually have two types of gaps. You have line gaps, which are actually very similar to gaps that you have in a Hermitian model. And you have so-called point gaps, which means that you cannot shrink your bands, or you can shrink your bands up until a point, and you can thus define a so-called spectral winding number with respect to your base, to a base energy. And this is a truly non-Hermitian phenomenon that cannot appear for Hermitian systems. And like I said, it can be seen in the spectrum, or it can be seen by the fact that you have a non-trivial spectral winding number. And it turns out that if you have such a non-trivial spectral winding number, that you break the bulk boundary correspondence in the sense that you always have a skin effect. So you always see that your bulk states under open boundary conditions pile up on the boundaries. Another way to see this is by looking at transfer matrices, which is what we did in this paper. And there we found that if your transfer matrix of your system, which you can use to find all the eigenstates and eigenvalues of your models, when this is non-unimodular, which means that the absolute value of the determinant does not equal 1, that you also break the bulk boundary correspondence. And actually, this is quite intuitive because the transfer matrix takes you between unit cells. And if the determinant, let me skip this because this is a bit too detailed for this point. But in any case, you can find it also there. Okay, so let's remedy this situation. So again, here you have the model, and now we're going to look for eigenstates of the following form. So this is the right eigenstate. And you see that this is very similar to the eigenstate that we found before for the Hermitian SSH chain. But now in the numerator, I have T1 minus gamma. Because this is non-Hermitian, you also have a left eigenstate. And here you see that it's different from the right eigenstate in the sense that in the numerator, you now have T1 plus gamma. And this you can easily see from this chain because the left eigenstate of your Hamiltonian is the right eigenstate of the adjoint of your Hamiltonian. And if I dagger my system here, I simply flip the sign of gamma, and this is indeed what you find here. And again, these RL and RRs, as they call them, you can also find them by making use of this destructive interference argument. We can then use these eigenstates to define a bi-orthogonal polarization, which will actually tell us what's going on in the system when I have open boundary conditions. So here's again the spectrum that I showed you before, and this is the object we're going to look at. So this psi R and psi L here, these are the eigenstates that I've written here. And what we're going to do is we're going to take a so-called bi-orthogonal expectation value of this object, where M labels your unit cells. This pi of M is a projector onto each of the sublaticides in your unit cell, and capital M is the total number of unit cells that you have. And if we then take the the limit of the M going to infinity, we find that this P goes to 0 when RL, RR, so just to remind you, this is RL and this is RR, is larger than 1. And you can find this by just plugging in these equations. And you see that this indeed corresponds to regions in the spectrum where you do not have a end state. When this RL-RR object is smaller than 1, you indeed find 0 energy end states in your spectrum, and P jumps when RL-RR equals 1. And this is exactly the same argument that we used before. When this happens, somehow your states need to attach to the bulk bands, and that's indeed what you see in the spectrum. And this we call a bi-orthogonal bulk boundary correspondence. As I mentioned, these systems are extremely sensitive to boundary conditions, so you may wonder, how sensitive are they? So we also check this. So if you couple the ends of your systems to each other with some term gamma, and then you start varying this gamma, you can sort of see, when do I lose this physics from the open boundary condition spectrum or open boundary condition case, and go to what you would expect from periodic boundary conditions. And you actually find that already for very small crossover gamma, as we call it, which goes exponentially with the system size. This then makes you wonder, okay, how physical is this? If I very weakly couple my ends, I immediately lose all the interesting features that I just described. It was shown in this paper last year that as long as you take locality constraints into account, which is in physics quite normal, then this kinds of coupling between the ends is completely suppressed, and you actually will find the physics that I talked about. Another thing we checked is what happens if you have domain walls instead. So now you couple a non-Hermitian chain to a Hermitian chain, so just a Hermitian SSH chain, and then you vary the gap in this Hermitian chain and you see what happens. And when you have a large gap in the system, you will see, this is a spectrum, that this is very similar to the one I showed before, that you still have these zero energy end states in the region where you would expect them to exist under open boundary conditions. However, if you then start reducing this gap, at some point you have a so-called crossover gap, then the zero energy end states, they already start to disappear. And once the system is gapless, you actually find something that's much more compatible with what we know from the periodic case. And this can be really understood from the fact that the bulk states pile up at the ends, and once you start closing the gap in the system, they can tunnel through. So I already mentioned there are some experimental realizations of this chain. So one would be in topoelectric circuits. So these are classical realizations, I should say, where you can get this type of hopping by using amplifiers and resistors. Another place where this was realized, and I should say that I should have updated this reference, this is now published, is in active mechanical metamaterials, where you have robotic systems where they can also realize such non-reciprocal couplings. And similarly, there's also a realization of these non-reciprocal couplings in a quantum walk, in a non-unitary quantum walk, I should say, such that when you have the non-unitary quantum walk, the probability that you end up on one of the ends is much higher, and which is what you see down in this row here. And this is also signals this skin effect. So what I just told you about this biorthogonal polarization for the one-dimensional SSH chain can also be generalized to higher dimensions. So for example, to non-Hermitian turn insulators, where you can also use this equation to find, for example, a phase diagram, which then tells you how often, in this case, your chiral edge states attached to the bulk bands. Indeed, this is a picture of this phase diagram. So where in the white region, you have 0 attachments, which you see indeed in the spectrum. Here in this light orange, you have 4 attachments. Here in the darker orange, 6, and in gray, you have 2. And this is exactly corresponds to what we find. And this is also the picture that I showed you on the first slide. That's actually this model. You can also do it for higher order topological models where you have boundary states localized to higher order boundaries, in this case hinges. So this lattice would represent, if you think of each side as a one-dimensional periodic chain, this is a 3-dimensional sample with open boundary conditions in 2 directions with hinges. And here you can also make use of this biorthogonal polarization to understand what's going on. So the non-Hermitian model realized here also breaks a form of bulk boundary correspondence, in the sense that the system under periodic boundary conditions shown in gray behaves very differently from the one under open boundary conditions shown in blue and red. And also here you can make use of this biorthogonal polarization. Moreover, if you have multiple boundary states, then you can straightforwardly generalize this equation to take that into account as well. And indeed here, for example, for a system where you either have 2 zero energy end states in this region or 1 in these regions, you see that the polarization captures this very nicely. And with that, I would like to conclude. So I hope I've shown to you or convinced you that non-Hermitian Hamiltonians possess many unexpected features, that gap closings are generic in 1 dimensions in the presence of symmetries, that you can define a biorthogonal bulk boundary correspondence directly in systems with open boundaries. And again, if you're interested to learn more about this, I would like to refer you to our review paper. And with that, I'd like to thank you for your attention.
Thank you very much. So is there any question? Anyone wants to ask anything? Okay, so Lavi has raised his hand. Okay, let me... Yeah.
Hello.
Okay,
Can you hear me?
Yes, please.
Yeah.
Go ahead.
Yeah, so actually I had a very naive question. So what I saw in your non-Hermitian skin effect, I found it to be more like a 1D property. I was just wondering if you extend it to 2D, do you have like some flow of like in this on a 2D plane or something, or it's different?
No, that's a very good question. Yeah, so you can have it in higher dimensions. So here I don't show you at all what model we consider, but this non-Hermitian churn insulator, which is a two-dimensional model, has this effect as well. In this case, the skin states would sort of go over the plane and live on the one-dimensional edge. But also in this higher order model, actually you have a skin effect, and here they pile up on the hinges.
So it's, I mean, in that case, you may decide where you want to have non-reciprocal hopping, like along x-axis or along y-axis. So, yeah. Okay, I see. Okay.
Yeah. So yeah, you can really engineer it in these type binding models that way. Yeah.
Okay. Thanks.
Anyone else wants to ask any question? Maybe I would like to ask one. So you consider a very specific way of non-hermeticity. You have this hopping go to the left and to the right, which are not the same. So yeah. If you consider other kinds of like situations, you lose the main effects, or is this something very general that happens every time you have some kind of non-Hermitian?
Yeah, no, that's a good question. So the answer is no, it doesn't always happen. So in this models, it's very obvious to see that it happens, right? Because I changed the magnitude of the hoppings inside the unit cell. There's other models where you can generate the same thing where it's not so obvious. So for example, this paper I referenced here, there a different model is considered, which is a non-Hermitian Kreuzladder model, where you actually have on-site gain and loss, but that model actually turns out to be unitarily equivalent to this model. So you actually find the exact same spectrum there with the same properties as for this model. But when you look at the model a priori, it's not so obvious that this is indeed what happens. And really the way to see it is really by the fact that you have this point gap spectrum in the spectrum of your Bloch Hamiltonian. And you can find the non-spectral winding number. And this then is an indication, okay, this is sort of like the topological invariant that tells you you're going to have a skin effect.
Okay, there's another question from Clara Bonjura. Maybe you can ask it directly, Clara, if it's okay. Please go ahead.
Can you hear me now?
Yes.
Thanks. Thanks for the nice talk. Really interesting. I was wondering if there are systems where you can have both a point gap and a line gap. So if you said that point gaps are truly non-Hermitian, but is it possible to have a mix of both, essentially?
Yeah, actually, in a way, a line gap system already also always has a point gap, in a sense, right? You can define a point on which the bands do not cross. However, so actually this SSH model that I showed actually has this kind of system where this is sort of open. So you have two blobs of these kinds of bands. So it has basically, you can define spectral winding number +1, -1, depending on where you are in your system. So yeah, you can.
That's really interesting. Thanks.
Okay, maybe there are two more questions. I will allow one more, and so that we keep on track. So I have Joaquin Medina first. I don't know if this was by the order, but please go ahead, Joaquin.
Hello,
Hey.
Can you hear me?
Yeah.
Okay. I'm thinking this more from an optical platform. I'm viewing this, and I think Alberto already addressed the questions I want to ask. So one is you make the hoppings complex. So how could you achieve? What would that represent in a physical system? Because non-hermeticity on the on-site energies is gains and losses, but on hoppings is my question. And the other is the non-Hermitian skin effect. You would have all eigenvectors grouping to one boundary. So what would happen if I shoot an excitation to this lattice on the bulk where there are no eigenvectors? Would it move to the boundary, or does it not propagate and just die exponentially? So those are my questions.
Yeah, so thank you for your question. So for the first one about how to sort of realize these kinds of terms in an optical setup, I would say that's not so straightforward. Of course, I mentioned there is the experimental realization in a quantum walk, which is an optical setup where they do this using non-unitary quantum walks, but that's a bit different. It's not really the type binding realization. It's more that you have the same type of systems realized. I think in principle, it's not so straightforward to see how you can realize these kinds of terms in any optical setup, but like I said, it's unitarily equivalent actually to a model with on-site gain and loss. So you could, for example, realize that. And yesterday there were lots of talks on how to realize these non-reciprocal terms in optomechanical setups. So I suppose that one could use those kinds of techniques. Then to the second question, how the excitation would behave, that's actually a very good question. I'm not entirely sure. It's probably, someone has probably looked into this. I just don't know the answer off the top of my head, but I'm guessing that it's the first thing you said, that it would propagate to the boundary, but that's a guess. Yeah.
Okay, thank you very much.
Yeah, thank you.
There was an experiment from the group of Samait, a paper published, Funneling of Light, Topological funneling of light. I think they addressed this exactly this question experimentally.
Okay. Perfect.
Very nice paper. Okay, so I would okay, maybe we, if it's a quick question, Gunnar, go ahead, please. Let me activate the sound. Please.
A very similar question to the previous one.
Okay. So then we skip it.
Yeah.
Okay. Yeah, thank you. Sorry about that. Thank you very much.
All right. Thank you.
Thank you, Flore. Thank you very much.
Yes,
so we let's move to the next talk. So the next talk is by Beatriz Olmos. Okay, there it is. So you can see the title: Implementation of a long-range SSH model in a waveguide QED setting. So please, Beatriz, the word is to you.
Thank you very much. I am not going to ask the typical question, do you see my screen and everything? Because yeah, it's the most asked question this year, I think. So yeah, I'm here to talk to you about implementation of a long-range SSH model in a waveguide QED setting. I think, yeah, this is a rather general title, so let me walk you through it. So this is a work that I have been doing during the last year or so with, okay, what I will be talking to you about is a bit longer than that, but okay, I am now based in the University of Tübingen, and I have been doing this work. I mean, Kieran McDonald, who is also here in the audience today from the University of Nottingham, has been doing really the heavy lifting in this topic. Good, so because we are in this conference, Topology meets Quantum Optics, and we have heard a lot about topology. I will end up with topology, but first I'm going to tell you a bit about quantum optics, which is the system, so to say, because that we use in order to do this work. So first of all, let me tell you which kind of quantum optics I'm talking about when I say quantum optics. The system that I will be considering here in this most general form is actually a system of neutral atoms that are generally in low-lying states that are interacting with the radiation field. That's, as I say, it's a very, I know that it's a very general, so to say, way to say this, but this is how it is at the moment. Now, what kind of systems are comprised here? Well, we have heard already a couple of talks about this. For example, okay, we had, for example, yesterday, Antoine was talking about this, Antoine Robet, and also Alejandro was talking about it yesterday. But okay, basically what I'm talking about is anything from just atoms that are coupled to the radiation field in free space, or that are trapped in a lattice and are still coupled to the radiation field. I could be talking about atoms that are close to a surface, for example, or to a bunch of, a couple of surfaces. And what I will be eventually talking about at the end, where you have a nanofiber or some sort of waveguide nearby the atoms, and then you have them coupled not only to the radiation field, but also to the guided modes that are carried by this nanofiber, by these waveguides. You can see here, I'm a theoretician, so all of my atoms are two-level systems. Sorry about that. Later, I will complicate it a little bit later, but okay, I just want to tell you what I work with. But all of these systems, what they have in common is that in its most general form, they have long-range dipole-level interactions that are driven or induced by the exchange of virtual photons with the environment be however it is, and I will go into detail later. And these systems also have collective dissipation. That will play less of a role for quite a while, but it will come back to us. So this is, as I say, this is my working horse of most of the research that I do. And the good thing about this is that there is one equation that rules them all, which is the master equation. So again, just to give you an idea, what happens here is that I have a bunch of atoms and I plot them here as these blobs, so to say, and then they are coupled to some environment, which I plot here as this blue background. And then what I do is, okay, you know all about this. I obtain a master equation by tracing out the radiation field. As I say, I don't say anything about the specifics of the radiation field, but I will say some things in a moment. So the equation that I will be working with all of this time will be just this master equation that you all know. And this is just the density matrix that describes the internal degrees of freedom of these atoms only. So I kind of got rid of the light, so to say, I got rid of the radiation field. And but this master equation obviously is going to be valid for everything that I show you today, but one has to keep in mind that this is only valid under some approximations like the dipole approximation, Born-Markov approximation, rotating wave approximation. Good. So as I said before, there are two kind of processes here that happens, the collective dissipation and the dipole-dipole interactions. So I just show you very quickly here what this means. So this Hamiltonian here is basically going to be this Hamiltonian, where these sigmas are just, the ladder operators. So these are spins, okay? I have my two level atoms. As I say, I will complicate it a little bit later, but these are my hardcore bosons or my spins. And I have here the ladder operators. So this goes from the excited state to the ground state, and this one vice versa. And then there are these VJLs, which describe how strong these interactions are. So this is just a hopping, basically, of an excitation from one atom to another via an exchange of a virtual photon through the environment. So these are the dipole-dipole interactions. And then what I also have is collective decay. And I just flashed it here because I'm not going to go too much into detail about this, but basically this is how this D of rho looks like in general. And then the decay channels and decay rates out of these, if the atoms have specific configurations, can be either superradiant or subradiant, which means that they decay. So there are atomic states that you can excite that actually decay much faster than what a single atom would decay normally, call it gamma, or subradiant states, which are usually more interesting because they allow you to trap the light, so to say, in these systems for a very long time. And again, this is just atoms coupled to the environment, and all of these effects, so the dipole-dipole interactions, the collective decay, they all come, so to say, for free, which is what I find make this kind of system so exciting. Of course, this is, again, I have been very general because I wanted to give you this equation that rules them all. But now the specifics, the devil is in the details, and now specifics of how these VJLs and these gamma JLs look like, and hence how my system is going to look like. In particular, I'm going to focus on this Hamiltonian a lot. So I will be interested in how these VJLs behave. They will depend on many things. For example, the atomic dipole moments, so the specific polarization. It will also obviously depend on the radiation field structure. So it's not the same to have the atoms in free space or to have a waveguide QED setting or have some surfaces around. And also it will depend strongly on the geometry of the atoms. It won't be the same to have a disordered gas or have ordered arrays in 1 or 2D. So now, okay, I focus on a specific system in which we looked now at topology, right? So we use this system, and in particular, we looked first at atoms in free space. And okay, I mean, I just give you this reference. This is something that we did already some time ago in 2017. So also a similar system was already spoken about yesterday also. So similar to this system, but a bit different, and you will see in a second why. So what happens here that we considered is atoms in free space, but they are in a 2D configuration in an optical lattice, which looks like that. And then in general, whenever I say A, I mean what's the nearest neighbor distance between two atoms. And now, as I said before, I was going to complicate things a little bit. I have a single ground state and I have two excited states, minus and plus. And this is lambda, which is the distance, what determines basically the energy of between the ground and the excited state. Good, so then here, the Hamiltonian is as I say, I'm going to focus mostly on the Hamiltonian. I'm just going to take for the moment dissipation, and I'm going to put it in my pocket. I will take it out again later, I promise, but for the time being, it's just not going to be relevant. So I take the Hamiltonian that describes the system, and it looks very much like the one before. It's just that now I have these Ds, which are nothing but, the ground state going to the plus state and the ground state going to the minus state. So I have to define these as vectors, basically. And of course, then these interactions are actually a matrix, and I have some interactions between the minus minus and the plus plus, and I also have these interactions. And again, this was already talked about yesterday briefly. I think it was by Alejandro or by Antoine. I'm not sure completely, sorry. Good, but now, okay, here comes so far these are functions, right? But now these functions, when the atoms are in free space, and in particular, I'm considering dipole moments that are lying on the XY plane, okay, just for information. Then what I have is that these functions are actually functions of something, and this KJL is actually is called the reduced distance. So they will be depending on the distance divided by the wavelength of this transition. Okay, so this is, which means that these interactions, or this hopping, so to say, this is going to be stronger, or will happen more often, so to say, the closer the atoms are in these lattices, which is something that one can do actually experimentally nowadays, which is really, I don't know, I find it really exciting. But you can see here that, okay, usually what you consider is this strong term, which is 1 over r cube, so to say, but there are also other terms that we will come back to in a second. So what happens here is, anyway, so far, what we wanted to look into is, okay, does this system have topologically non-trivial phases that might be worth having a look? But then, as we know, there's this classification of Hamiltonians, and then, because this system is symmetric under time reversal symmetry, we know that this is topologically trivial. And then what one does is, to break this time reversal symmetry, this is in 2D. And then we do that by using a magnetic field that is perpendicular to the lattice that breaks the symmetry between the minus and the plus state. And as a consequence, what you obtain is something that indeed is topologically non-trivial. These are basically the bands that you obtain out of these. And these are the Chern numbers of the 4 bands. And you can see that depending on the strength of this magnetic field that is perpendicular to the lattice, you will get different Chern numbers, and of course accompanied with corresponding edge states. And here we see that indeed, we have these edge states coming up, and one can calculate them by basically, as you all know, breaking this bulk into a semi-infinite strip. And then I have here, whatever lives on the blue side and whatever lives on the red side. And you can see that these states here, these edge states that cross these bands, cross from one band to another, these are edge states. And we wanted to see also, on top of that, whether we could actually excite these states. And then we did this in a very non-equilibrium way. So what we have is, we consider a finite lattice that looks like that. And then you shine a weak laser on this. And then what we see is that, okay, if you drive weakly this atom on the edge, then, and without the tuning such that it matches the energy of in this gap, then in principle, you should be able to match one of these edge states. And indeed, what happens is that we see that this is kind of the population as a function of time. So this is for one time, this is for another time. And then you see what happens in the steady state. As you continuously drive, you can see that this edge state is actually occupied. And on top of that, in this particular case, what we did is we took back then dissipation into the problem. And okay, first of all, we check that when you put defects into the lattice, still this edge state remains, which is what you can see here. And then we also added dissipation, and then what we saw is that these states on top of that, they are superradiant, which is kind of the cherry on top, because it means that you can actually have them for a very long time, and they will be relatively immune to the dissipation. So if you have a photon that it's in this edge state, it will remain there for a very long time. So I did say before that I would come back to these terms in these A's, right? So you can see here that, okay, we have actually long range interactions. And what I mean by long range is that you have a 2D system and you have something that grows as 1 over R. And as a consequence, what we found then, we analyzed these things. And then what we found is that there were some caveats and how to calculate even the Chern numbers and even the band structure. For example, here we found in a square lattice that one had actually one-sided divergences within the Brillouin zone. So this kind of, it's a motivation, so to say, and this led us to think about, okay, this is interesting because, okay, even though we have these long range interactions, so fundamentally long range, one can still see the same, one can still see these edge states popping up. And then, okay, our idea then kind of brewing started to be, okay, how far can I take this? Okay, because in principle, I know that this boundary correspondence and everything is there. You should still see these edge states, but okay, there is a point where your interactions are so long range that things are not really clear anymore. In order to study this further away, so to say, with longer range interactions, we came back to a system that we have been studying for other reasons as well. And I have to give you a small tour through guided quantum optics that thankfully, I think most of you know, but okay, this is the system that I will be considering. So this is an array of atoms, again, A here. And what happens here is that I have a nanofiber, which means that all of my interactions and also my dissipation can occur either into these guided modes or to the unguided modes of the radiation field. So if I am lucky, and this is what I'm going to be considering later, I will be mostly coupled to these guided modes so that all of my interactions and everything will be driven by these guided modes of light. So these coherent and incoherent couplings, the good thing about having them in this nanofiber is that actually they give rise to all-to-all interactions, which means that you lose completely basically the concept of space, so to say. So your interactions basically do not depend on how far these atoms are from each other, but rather where they lie, so to say, in phase space with respect to each other. So where this one corresponds to this one in terms of what's the phase mismatch between them. So this is interesting also because in these systems, you can actually also, and here comes the funny thing, because what says is that is chiral, which is a bit of a funny one because it's exactly when you break chiral symmetry, so you have a preferred direction. So you can actually choose your polarizations of your atoms such that you are either, and I'm going to use the proper wording, chiral, so that you emit photons or that you have no preferred direction to the right and to the left, or you can actually do this differently and then you have a preferred direction of travel of the light. So, and that these are systems that are actually done experimentally, as most of you for sure know. And for example, I cite here a few papers, but also what I wanted to say is that this is not the only system that where one can look into these all-to-all interactions. And for example, these photonic crystals, and there are also these waveguides where you can actually see these effects as well. So what was the idea? Our idea was to basically put these two things together. So you have these systems, and we can study basically topology in the presence of really long range interactions. So what happens if you have all-to-all interactions? That's basically the idea. And now I kind of walk away for a second from these waveguides and I tell you what the system that we're looking at is. So we wanted to look at this kind of extended SSH model, and I cite this paper here because we will be stealing a bit of the notation from that. So what is the idea? Okay, we have these two sublattices. You have already seen this SSH model already a number of times. So, okay, basically you have this red and the blue sublattices, A and B. And then what I will have is that my interactions are basically all-to-all. So everything can interact with everything. In order to write this down, what I have is that this H is equal to the sum over J and over I and J. And then I have these couplings J that depend on the distance between the atoms. And this is what, again, will happen later when I have the waveguide. Okay, so that's how I kind of make the link. And the Ci dagger and the Cj are just bosonic operators. So the thing is, they disappeared all of a sudden. Sorry about that. I'm going to use this way now of calling these couplings. So I'm going to separate them into, okay, the ones that happen, so to say, from the red into the blue. So these are going to be the primes. So these are these J primes here. So this is when the distance is odd, so to say, and an odd number of sides, if you want, and there are p of these cells apart. And then this is what happens the same, but when there are p+1 cells apart. So this is J1, and this one over here that you can also see here is J1 instead of J1 prime. And then I am also going to go J2p, whatever interactions happen between the same sublattice. And then, okay, my Hamiltonian, just to cite you, what happens is can be rewritten like this. So M is the total number of atoms, and M/2 is the total number of cells. So I have now introduced these A's and B's as the bosonic operators that create and annihilate a particle basically in each one of the sublattices A and B. So why do I use this? Because this system now can be recreated approximately with 2 offset arrays of atoms coupled to a nanofiber. And this is basically how it looks. So I have now my nanofiber, and now I have my atoms here. And what you can see is that I have 2 chains that have the same distance here. So this could be A and this could be A. Each one of these atoms is a 2-level system as before. And then what I have is that they are offset by some quantity B. Now that difference, so to say, that offset will be what allows me to differentiate the J primes and the J's basically. And in particular, for one of the systems that we are going to be looking at, so we will consider, for example, the dipoles all aligned with each other. Here, for example, these JPs, these J2Ps and J2P primes and etc. can be written like this. So they look just like a sine function of some kind, okay? Don't want to bore you too much with the details, but basically you can control up to a point how these interactions look like. Even if you're lucky, actually also canceling these J2s, these even hoppings that, as you know, usually break. Okay, this just breaks the chiral symmetry of your system, and then usually, gets rid of the topological order. But I will tell you about this in a second. So first of all, we wanted to check that this system actually recovers the SSH limit. So if you have just, as I say, you have just J1 and J1 prime, then you should recover that system. And indeed, this is what happens if you change now this offset, this B, and I divide it by A. What you can see is that you either have topological, this Chern number, so to say 0, or you have it 1, depending on the ratio of these two. And this corresponds actually, this ratio of these two corresponds to having J1 bigger than J1 prime, equal somewhere here in the middle, and here on this side, you see that you have the other limit. So this is literally just an SSH model. And you can actually see this also by looking at the localized, at the edge states, which are over here. And then you can see that they are exponentially localized. And this exponential localization, this localization length will obviously change depending on where you are in this B over A, which is the same as saying how big J1 is with respect to J1 prime. And this line over here is just this logarithm of J1 minus logarithm of J1 prime. So you can see that the localization length really corresponds to what happens in a normal SSH model. Now, again, okay, these kind of ideas were already discussed in this paper, in this very really nice paper. What happens now when you break chiral symmetry? So you add this now, these next nearest neighbor interactions, so these J2s, and then, okay, we break it just a little bit because we can do this also, we can control this up to a point by controlling how far the atoms are from each other, actually, so we can do that. And then if we break it a little bit, then what happens? And again, I'm just considering nearest neighbor, next nearest neighbor so far. Then what happens is that, okay, even though you have this, you're supposed to say to break completely this chiral symmetry, and as a consequence, you should be in an A1 group, so to say, a classification, and then you shouldn't have any edge states. Indeed, what happens is that you still get them as long as you are in a phase where, okay, this is just a direct gap, this is a direct gap, this is an indirect gap that you get over here. But then you get to a point where this band is pushed up so far that you don't get any gap anymore, you're in a metallic phase, and this, okay, this is already described by these inequalities here between the J2s and the J2 and the J1s. The edge states also obviously lose a little bit of their edgy component, so to say, but you can still, in some regimes, still observe them happening. So I'm going to just skip through these, so to say, and then I'm going to actually look into what happens when you have all-to-all interactions, which is what we are. It is basically the work in progress. So what happens here? Now we really consider all-to-all interactions, all of them. But we are, for the moment, going to be in a regime where the chiral symmetry has not been broken. So it's all of atoms that belong to different sublattices are connected to each other. And then here, I'm considering 14 nearest neighbors just so that you see that, okay, here I have 100 atoms in my chain. Then, okay, here I'm increasing and decreasing the system size, okay? And which means that effectively what I'm doing is I'm making my interactions longer and longer range in a way. And here what I have is literally 14 atoms, and then I have 14 nearest neighbors. And what you can see is that even in this case where everybody's talking to everybody, so to say, when you have really long range interactions, all-to-all interactions, you still get these edge states surviving. And you can see here that this is basically the edge state that you get. This is one of these two. What you can see is that they are still looking, they look a little bit different from the usual edge states, which I would also expect somehow, because even the very definition of an edge here is complicated because all of the atoms are talking to everybody. And this is something that we're still also investigating how to explain. But they are also present. And we also check that these are also robust with respect to disorder. So when we move the atoms away from their positions, they are still there. And if you increase the system size and increase the system range accordingly, these states still remain and they display basically the same features. So this brings me to my Outlook page, thank God, because I'm running out of time. So I wanted to tell you a little bit of what still has to be done. So first of all, what we have a look at is what happens now if you really break also chiral symmetry. And what happens there is that even though, we lose, so to say, the original edge states, actually we get some different new edge states. Over here, for example, you can see this one here, and this is the edge state that are actually much better exponentially localized than the others, and that are also very much robust against disorder. So this is something that we still need to investigate. Then we also need to investigate what happens when you add, again, dissipation. And you can do this by, for example, what Flora explained before very nicely, by investigating what happens with the corresponding non-Hermitian Hamiltonian. That would be really interesting. Or by, as I said before, adding dissipation again and looking at how these states evolve in time, if they are excited. And we will also have a look at what happens, because so far we have kept all of the atoms with emitting with the same directionality into the lattice, into the nanofiber. What would happen if that was broken? And with this, I thank you for your attention. Thank you very much.
Thank you very much, Beatriz. So I see already 2 questions. So please go ahead, Alejandro.
Yes, so I was wondering, like in this waveguide case, so are you considering only the infinite range interaction with the waveguide, or also the dipole-dipole couplings with the free space environment?
So far, we are only considering because it was supposed to be a toy model in order to understand this topology in all-to-all interactions. We only considered the one within the nanofiber, but again, the machinery is there to also consider the rest. The problem there, of course, is that you start losing some photons into the environment, and that cannot be really avoided. And then one has to be clever in order to excite states that are particularly also dark with respect to the radiation field. Yeah.
Thanks.
Okay, Paloma, please go ahead. Oh, sorry, I will not touch it anymore. Okay, now
finally.
Yes.
Thanks, very interesting talk. So I was wondering, because I think there are some connections to the problem that I have studied with classical dipoles. And I was wondering if your which polarization you consider for your emitters in the waveguide case, or are these longitudinal or transverse modes?
At the moment, we are only considering the dipoles, basically, if they, I do it with the hands because it's easier. So I just do the nanofibers here, and the dipoles are perpendicular to the lattice, to the nanofiber. Obviously, the logical thing to do now is to introduce also circularly polarized light and see what happens, as I say, when the directionality of the coupling, so to say, it's broken there. And there you can really get basically. I thought that maybe you can actually lift the degeneracy between the two sublattices, and then something interesting might happen.
Okay, thanks.
Okay, thank you, Beatriz. And last question by Mohammed. Please go ahead. I need to go ahead. We don't hear you, Mohammed.
Does it work?
Now it works. Now it works. Yes.
Thanks for a very nice talk, and I apologize if I missed that in the first part of the talk when you showed that you have the edges and you could find the topological property. Was it only for a single excitation manifold?
Yes, no, you didn't miss it. I forgot to say it. I realized later. Yes, it is in the single excitation manifold. Yes.
And do you have some ideas what would happen for two excitation, and how do you characterize such states?
I know I don't. No, I don't have a good answer to that. This is something that we also want to investigate, because it's kind of the logical next step, so to say. Yeah.
Okay.
To see whether topology also survives this somehow. Yeah.
Thank you.
Thank you very much. So I think we can thank Beatriz again. Thank you. And now let's go to the final talk of the session. So I think Mikael is there.
Hi, everyone.
Hi, Miguel. Great. So please try to share your screen.
Yeah. Do you see that?
Yes, perfect. So the final talk of this session is by Mikael Rexman from Penn State, and it's about nonlinear topological photonics. Please.
Okay, thank you so much, Alberto, and thanks to all the organizers for the invitation. All right, let me get started. The title of the talk is Nonlinear Topological Photonics. I'm going to be talking in particular about one highlight of recent research on topological pumps. And if there's time, then I'll get to some of our work on bulk and edge solitons. So these are my group members. This is actually an old picture. Alex has just moved on to Sandia, and we have one or two new young grad students. So this is core members of my group, and I'm going to be talking in particular about the work of Marius and Seba Mukherjee. Okay, so as I said, I'm going to present two aspects of nonlinearity in topological photonics. The first on quantization of Phallus pumps via nonlinearity. This is a case where nonlinearity actually acts to induce quantization where you wouldn't have it otherwise. And then, time permitting, I'll talk a little bit about solitons. I don't think I will have that much time at the end, but I might just sort of scan through some of our recent results. Okay, so let's see. Part one is on quantized nonlinear Phallus pumps. Here we go. I think for this audience, I don't have to give too much of a background on topological photonics, but I'll just say very quickly that this was an idea that was pioneered by Duncan Haldane and Sri Raghu. Their idea was to use a magneto-optical photonic crystal structure. So as opposed to something like glass or silicon, to take a garnet type material, impose a strong external magnetic field that breaks time reversal symmetry, and then you induce these chiral edge states, as many of us know. And then this was realized in the microwave scale. So you see the unit cell there is 4 centimeters. This is a big old thing. It was realized by Marin Sojocic in a ferrite material, where he observed these edge states propagating with microwave photons. And then a bit later, my work, along with Moti Segev and Alex Samite, showed that we could realize this in the optical using coupled helical waveguides. And Mohammed Hafezi's work using coupled ring resonators showed that you could realize this on a silicon chip in the optical regime. So we could actually go from this very long scale wavelength down to optical wavelengths. The technology that we use are femtosecond direct laser written waveguides. The fabrication process looks something like this. So you have an ultrafast laser that focuses into a piece of glass. You locally ablate the glass using a multiphoton process, and that locally increases the refractive index just by a little bit. Something on the scale of between 10 to the minus 4 and 10 to the minus 3. And by dragging the sample through the focal spot, you induce a waveguide. And the waveguide is very similar in many ways to an optical fiber. The properties are very, very similar. They're single mode. If you get them close enough, they can couple to one another. And it's not too different. So if you're familiar with optical fibers, then you're going to be familiar with these types of waveguides. Of course, it's much shorter than a typical optical fiber. It doesn't go across the ocean. It goes over the course of several centimeters along this integrated chip. Here's just a picture of a mode. It's a single mode waveguide for one of these waveguides. This is a picture of a lattice of them at the input facet, and then this is just the coupling function as a function of the distance between neighboring waveguides to show that if you put them close to each other, they couple strongly. If you put them more farther apart, then they couple more weakly, and the functional form is exponential. Just like nuclei in solid state materials. The diffraction of light through this structure follows a paraxial Schrödinger equation, described here, where the time coordinate is replaced with the z coordinate. So the length of propagation along the waveguide axis, that acts as a time coordinate. Otherwise, it's very, very similar to standard Schrödinger equation, where the increase in refractive index of the individual waveguides induce a potential well in which you can have bound states. And if you put those, as I said, those potential wells, those waveguides close enough, then they talk to each other. You can have hopping between them. So you're basically emulating the temporal dynamics of a two-dimensional material. All right, and so this is really what you see. If you have a honeycomb lattice shown here, and you start by injecting light into a single waveguide, then as a function of the propagation coordinate z, the light spreads out from side to side to side and spreads through the lattice. So this is perfectly analogous to taking, a piece of graphene, if you could do this, and putting a single electron into one of those PZ orbitals and then watching it spread out in time. So we're basically emulating a two-dimensional material here. Okay. So we really wanted to ask about the case of interactions. There's been so much work done in the non-interacting case in topological photonics. And we're really curious about the interplay between nonlinearity and interactions along with topology. So what if you have a Hamiltonian that is topological in some sense, and then you have this nonlinear term that's associated with the Gross-Mitievsky equation? This is a very, very general equation that describes interacting bosonic systems and the mean field limit. It really comes from the Bose-Hubbard model, which describes ultra-cold bosons. And it's just very, very general, very applicable across many different bosonic systems, including exciton polariton condensates and others. What's going on here is that the wave function itself, so the field itself, induces a potential in which it evolves. So that's the sense in which you have interactions, is that in the specific context of our system, when we turn up the power a lot, we get Kerr nonlinearity. That nonlinearity induces this potential, and then the wave function is therefore evolving within the potential that it creates. In that sense, this is topological nonlinear optics, as long as the Hamiltonian is topological. So I want to talk about solitons. These are really, the first thing that you think about in nonlinear Schrödinger equation, very fundamental entities. So these are self-guided waves. They are guided by the potential that the wave function itself creates in a self-consistent sense. So the wave function creates a potential, and then the eigenstate of that potential is the wave function which induces that potential in this kind of self-consistent loop. And so it really is a self-induced waveguide. This was discovered in Scotland by a naval engineer in water waves, more than 100 years ago. And you can see it very, very clearly across many, many different systems. This is really what sort of a paradigmatic example of the soliton here. This is the case where you have no nonlinearity. You see a wave packet just diffracts, and of course, the smaller it is, the more quickly it diffracts. But when you do have nonlinearity and you get the right functional form, then it induces a potential in which itself it's guided. So it's a self-induced waveguide. And to see how general solitons are, all you have to do is do a quick modulation instability calculation, which I did here, which is to say you start out with some constant wave function to begin with just a little bit of fluctuations on top. And there's an instability, the wave function falls apart and spontaneously forms these solitons. So in some sense, they're very universal objects of this set of differential equations. They are, just a few points about solitons, they balance spreading with nonlinearity, as you can see here. They're in a precise sense, actually, a basis for many different nonlinear differential equations, not just the nonlinear Schrodinger equation, but also the KdV equation and others. They're ubiquitous across wave physics, both in fundamental studies and importantly in applications like passive mode locking, for example, and generating optical frequency cones. And so there's just these very important objects in nonlinear wave physics. I want to talk about some nitty-gritty experimental details in our system for us to be able to get nonlinearity. We wouldn't be able to do it with just CW light because we're using glass, which is very, very linear. Specifically, it's borosilicate glass. We really need to go to very high power to be able to get significant Kerr nonlinearity to get that nonlinear term associated with the Gross-Matievsky equation. So we have to use pulses. And so associated with that, we really have to worry about the temporal domain. We not only can think about Z acting as time now, but now we have to start worrying about, well, what's the pulse actually doing as a function of time? And the first thing to worry about really for us is self-phase modulation. What that is basically, you inject a pulse into a piece of glass. You get, because of the Kerr effect, you get this chirping of the pulse. In the spectral domain, what that means is a very quick spreading of the spectrum. And if you just naively inject pulses into a piece of glass to be able to get significant enough Kerr nonlinearity to see any effect in the lattice, you're going to get this very dramatic self-phase modulation. In other words, your spectrum is going to broaden to 300, 400 nanometers, but by 300 or 400 nanometers. And over that range of wavelengths, the coupling between waveguides can vary by more than an order of magnitude. So unless you manipulate the pulse before and you take care to do that, then you're going to get essentially many, many different systems all propagating together with completely different Hamiltonians. So what we did to remedy that is to first down chirp the pulse. So chirp it in the opposite direction, such that when you inject it, it unchirps itself over the course of the propagation. And as a result, you don't get too much spreading of the spectrum. So we start out with 8 nanometers and we stick by high power to still within 10 to 15 nanometers, at most 20 nanometers. So we are still staying within a range of wavelengths where the coupling is well defined. And that's really important to have basically a description by the nonlinear Schrodinger equation itself. Let me talk about Phallus pumps quickly. Phallus pumps, as many of you know, was really the first description of how you could get quantized transport from the quantum Hall effect. It wasn't phrased exactly that way by David Thylas originally. He was looking at one-dimensional model, which is time periodic, so it has a time-dependent Hamiltonian, which could be sort of thought of as this screw pump where you're sort of cranking the handle and pumping water up from the bottom to the top. So you've got just a one-dimensional Hamiltonian that does that. It basically takes, instead of water, it takes electrons. And what David Thylas showed is that you get this quantized amount of charge that's pumped over one cycle of the pump. And that turns out to be perfectly equivalent to a two-dimensional Chern insulator. So in other words, a two-dimensional system that exhibits the quantum Hall effect and the quantized conductance that's associated with that. It's just what is now called a dimensionally reduced version of the full two-dimensional model. So you dimensionally reduce to go from the full two-dimensional quantum Hall Hamiltonian down to this pump, or you can dimensionally extend to go from the pump up to the Chern insulator. Very important property is that was elucidated by David Thylas originally, is that you have to have filled bands to make this work. So in other words, you're making the assumption that your Fermi energy is somewhere in the gap, and you've perfectly populated the bands up to the top of any given band, and then Fermi energy is above that. So that perfect population, an equal population of each state in the band, is essential for the quantization of transport. So this is the Phallus pump model that we use. It's Aubry-André Harper model, an off-diagonal version of that. So here you see the waveguides. It's a schematic figure, obviously, but this is a real microscope image of the facet. They're coming closer and farther apart from one another during propagation. That's modulating the hoppings, because as I showed before, there's this evanescent decrease in hopping strength between waveguides. So as they get closer, the hopping gets bigger. As they get farther, the hopping gets smaller. And this band structure is just showing that this does indeed correspond to a Chern insulator in the higher dimensionally extended two-dimensional picture. And this is just a plot of the hoppings as a function of time, quote unquote time, or Z, during the pump cycle. So you can see that in the two-dimensional picture, there are three bands because there are three members of the unit cell, flux 1/3 model. And you've got Chern -1 for the lowest band, Chern +2 for the middle, and then again Chern -1 for the top. So what that means in the context of the one-dimensional pump model that you're seeing here is that if you evenly populate, say, this bottom band with Chern -1, with, say, a Wannier function, so an equal population of every state in the band, and then you let it evolve over one pump cycle, then it's going to pump to the left by one unit cell, by exactly one unit cell. So that center of mass is going to move over by one unit cell to the left. Why? Because it's Chern number -1. And that is really reflective of the quantized conductance that you would have seen in the higher dimensional model. Okay, so here you're seeing that. This is the perfectly linear case. We inject a Wannier function here at the top. These are simulations. So inject a Wannier function. It's hard to see, but this is a perfectly even population of every state in the lowest band. And you see, because it's a localized wave function, it spreads out as a function of time. But you get this perfect quantization of motion in the sense that the center of mass is moving over by exactly one unit cell to the left per pump cycle because it's Chern -1. And so you're seeing that in the plot basically over here. Now you turn up the nonlinearity. And what you see is that you also get perfect pumping, but now you have localization. So this is a soliton that's formed. It's changing over the course of the pump cycle because the Hamiltonian is changing. But if you can grant me a little nonlinear adiabaticity, which is not at all obvious, but I can tell you is true, if you can believe that the adiabatic theorem applies to nonlinear systems as well, then the soliton is just kind of tracking itself through the pump cycle and is realizing the corresponding soliton at any given point in the pump cycle. And then when you go to very high nonlinearity, everything just gets trapped. So in other words, you have such high nonlinearity, you're inducing incredibly strong potential well. And you're effectively taking the waveguide out of the system to form its own little subsystem of a single waveguide in which it has this highly localized solitons that doesn't move at all. Now, the key point here is the quantization. There's no reason to believe in the nonlinear case that this should be quantized at all. Why would that be exactly? In retrospect, to us, it made sense because we could argue this way. Well, we know that the Hamiltonian has to come back to where it started after a single pump cycle, right? So if there are only a small and finite number of solitons available, and that's actually usually only one for a given energy, then it has to either come back to where it started or come back to where it started modulo a unit cell. So it has to be quantized basically because there are only certain solitons available. And if there's only one available, then assuming adiabaticity and assuming that you're tracking a soliton all the way through, then it either has to come back to itself or itself shifted by a unit cell. And that's exactly what happens. Okay. So, a few little points here. So the nonlinearity induces the soliton formation. Here we're injecting a soliton, but you get spontaneous formation of the solitons. They are either pumped in the lower nonlinearity regime or completely trapped. So that's what we call them, the pumped and the trapped regime. If you look at the population of these solitons in the bands, so in other words, you take the soliton wave function and you project it onto the band from which it bifurcates, you get some power-dependent, model-dependent population. In other words, it's not equally populating a band, and yet it's quantized. So that's a little bit strange to think about. There's no equal population, but because of the nonlinearity, you have to get quantization. And another way of saying that is this, is that if we were to just take this wave function and evolve it linearly without the nonlinear term, then you would not get quantized motion. So there'd be no quantization. Okay. Here's what's going on in terms of bifurcations and nonlinear eigenstates. So this is a diagram here of the pump cycle starting up here and then looking at the center of the soliton as a function of z, the propagation coordinate through the array. So what you see is that the soliton starts out centered on A, and then it takes this trajectory and it goes through back to A. It has to come back to where it started, but modulo a unit cell, right? What you're seeing here and here corresponds to this slice and this slice at those time slices. And these are basically the available soliton solutions at those particular slices. The dashed lines mean that are unstable. The solid lines mean that they're stable. So you can see here that you only have one stable solution going all the way through. But then as we start the animation, power keeps going up. Something's going to happen. You get these nonlinear bifurcations, right? So now you've formed this extra possible path. Let me start that again. So by the time you're here, you've formed these extra possible paths because these new nonlinear eigenstates are now available. Remember, in the nonlinear case, you can get all these new eigenstates that you don't have to have the same number of eigenstates as sites. And then you go to higher and higher nonlinearity, and you reach eventually this pitchfork bifurcation up here, and you get the merger. So this one here, you get the merger of these paths. There we go. And what you can see is that that soliton path, because of the availability of new stable soliton solutions, has gone from pumping perfectly across from A to A, backwards by one unit cell, to being totally trapped at the site in which it was injected. And the mechanism is really the formation of these new solitons or new nonlinear eigenstates. So that's what's happening when you see the trapping. Okay. Now for the experimental results. So these are experimental results that you're seeing here in the top row. We inject in site A here. This is for pumping 1/3 of the full pump cycle. What you see is that when you inject, you sort of spread out and there's no quantization at low power. So this is the linear case. There's no quantization at all. You turn up the power, you form the soliton, and you get this pumping by 1/3 of the unit cell in this case, because this is 1/3 of the pump cycle. And then eventually it becomes trapped for higher and higher power, just as we predicted. Now this is 2/3 of the pump cycle, and you have similar behavior. No quantization at all. And then you see this soliton formation, and then finally trapping for very high power. Same for the full unit cell. You start here, you get some sort of random wave function. You see the trapping, so you see the pumping of the soliton for quantized in a quantized sense, and then it comes back and it traps itself for high power. Okay, so this is in line with what the simulations predict. Now, the question you can ask is does this only work for really small wave functions and for the bottom band? Is this some idiosyncratic case? And the answer is it really isn't. I can look, for example, at this model for all 3 bands, right? So there's the churn -1, churn 2, and churn -1. And what you see is there's soliton formation in each. And what you get is pumping according to the churn number for each band. You can see these wave functions can be very broad, actually. They can span 10, 20 unit cells. You still get this perfectly quantized nonlinear pumping, where you can see in the population of the band, which is shown in the insets, they're not uniform at all. And yet, because of the nonlinearity, they have perfectly quantized pumping. Okay. Now, a key question here that we don't have an answer to is why in the nonlinear case is it being pumped by the churn number? So we seem to find that the center of the soliton is, at least for low powers, is always in line with the 1e center, which implies that you always pump by the churn number. We've found that. We don't have a rigorous proof of that. So why that should be true exactly, that's still to us an open question. Why do you have, we know that it's going to be quantized, but why should it be quantized by exactly the churn number of the band from which the soliton bifurcates? That's not clear. Okay, so here you're seeing just sort of more numerical evidence of what's going on here. This is a topological phase transition that's just induced by changing the hoppings. And so you really sort of clearly see the effect. So here we have this trajectory where you're being pumped by 1 unit cell over the course of the pump cycle. And here's the animation. The bands you see are going to close. There's going to be a topological transition. And then at a certain point, you're going to see these trajectories kind of skew themselves, eventually break. Here they're breaking, and then they pump in the other direction by 2 unit cells. And that perfectly corresponds to the churn number of these bands. And so exactly at the topological transition point, the soliton is also undergoes a transition and pumps the other way according to the churn number of the band from which it's bifurcating. Okay, did I miss a slide? No. Here's another picture of what's going on. Solitons, especially for low power, take on the shape of the eigenstate from which they're bifurcating. And in this case, this is really the lowest eigenstate of the band. So it's meaningful to plot the soliton along with the lowest lying eigenstate in the band from which they bifurcate. We did that for each of the bands here. And so you're going to see that progress, the motion of the soliton and the eigenstate over the course of the pump cycle. And this is really instructive of what's going on. So you can see band 1 and band 3, the soliton is really taking on the character of the eigenstate. And that's also true of band 2. But what's interesting about band 2 is that you can see that that band is kind of, it looks like it's moving one way and the soliton is moving against it. Kind of like, you know, the bicycle wheel effect. All right, so this is a band of churn number 2. The eigenstate, this lowest lying eigenstate, seems to be moving to the left by 1 unit cell, but the soliton is moving according to the churn number and is moving over to the right by 2 unit cells, corresponding to +2 churn number. Oh, I see you, Alberto. I guess I'm out of time, right? What is it, 5 minutes?
No. We are really on the time. If you want a couple of minutes more, it's okay. Go ahead.
Okay, I'll just finish up. I mean, that's basically at the end of this part. So I'll just mention that in Seba's work, the previous work was by Marius and Seba together. In Seba's work, he showed the presence of Floquet solitons in the bulk of a photonic topological insulator system. And we also looked on the edge. And the bottom line with the edge, really, without going into all the details, because I don't have any time, is that one really has to face the problem of radiation into the bulk. You know, the minute that you have nonlinear effects, you know, you can have mode mixing. And why wouldn't the soliton on the edge mix with the modes in the bulk? And that's sort of the, you know, if we ever would want to use topological edge solitons to generate a really robust frequency comb or something like that, we will likely have to face the problem of radiation into the bulk and the associated loss. So that's going to be an interplay as we look at nonlinear edge physics, topological edge physics, that we're going to have to deal with, I guess, as nonlinear topological photonics progresses as a field. So if you're interested in this, you can ask about it, or I'm happy to talk to anyone later. And I guess I'll stop here.
Okay, thank you very much. It was very, very interesting. Really, I liked it very much. There's a question by Miguel Bello. Maybe you can say it loudly yourself. Say it loud. Okay, you don't have the microphone. Shall I unmute you?
Hi. Hello?
Yes, we can hear you. Perfect.
Okay, so I just wanted to ask you, why did you choose this 3-band model for the Phallus pump instead of, for example, a 2-band model? Like, is this model dependent, or is a general phenomenon?
Right. So yeah, that's a good question. We chose the model. You're talking about the Rice-Mealy model. Why didn't we use that?
Yeah.
For a very boring reason, which is it's a little bit harder to consistently get an on-site potential in these waveguides, which the Rice-Mealy model has. There's just more error in it.
Yeah, this is another question I had, whether it's possible to tune the refractive index along the direction set as you create the waveguide experimentally.
It is, and we've done it before. It's just not as precise. Like when you are just controlling the position, it's very, very precise what the couplings are. So that's the reason we chose it. Marius simulated something like, I don't know, 5,000 models or whatever, some huge number of models with, you know, different flux and all sorts of, you know, he put in random Hamiltonians, he automated it completely. And found whether they were a pump, found if he could find the solitons. It's not obvious that you could find the solitons, actually. But when he found them, in all of those cases, they always pumped by the churn number for every band for which he could find them. So this is really not a model-dependent thing. But we don't have a proof that it should pump by the churn number, as I said before. But, you know, it works in a zillion models.
Okay, thank you very much.
Okay, I have a question myself. So when you are when you explain very nicely the pump, the Phallus pump, and so you need to do it canonically, let's say like the way it was proposed at that time. You need to fill the bands. So you need to, your excitation needs to be a linear combination of all the eigenstates of the band, right?
Right.
Okay, and I think that's what you showed in the linear case. You have
yes.
the spread.
Yes.
But there is a degree of freedom here now. You can actually choose which linear combination exactly you choose. Okay.
Yes.
So I understand you choose a linear combination such that you pump only on one side, right?
It wasn't just one site. There was some support on neighboring sites, but yeah, very localized.
Yes,
yeah.
because you have ABC. Exactly, you're right.
Yeah.
So how robust is your nonlinear effects to this? So you inject a different wave packet that still is not too far from pumping the whole band. Do you get the same kind of like effects? Because I think when you go in the nonlinear regime, the shape of the initial excitation is very critical. Can be critical.
It can be, but in the nonlinear case, actually, you don't have that freedom because we're not injecting a 1A function. We're injecting the Soliton solution. And if
you're injecting directly the Soliton. Okay.
Yeah. Okay. So if you, especially if you're at low power, there's only one there, modulo the unit cell. So there's no phase freedom or anything.
Okay. I understand that.
So it's universal in that sense, but it only works for that one wave function, but that's the universal Soliton wave function. So that's what you expect. It's also true that, like, you know, imagine you just injected some random wave function. You know, you just pick any wave function and inject it. If it has high enough power, it's going to undergo modulation instability, and you're going to form these solitons, which will then themselves pump in a quantized way. So you don't have to try that hard, actually, to see this thing happen. It's very universal.
Okay, very well.
Yeah.
Okay, last question from Lavi. So please, Lavi, go ahead.
Hi, Michael. So I had a very naive question. So you were explaining about the nonlinearity in three regimes, like when you have no nonlinearity, weak, and the strong case. So what I was thinking is that, okay, the band structures were calculated when the nonlinearity was 0. Then we can define these Chern numbers. So in the weak case, you said these solitons, or like this quantization of the propagation of soliton was well aligned with these Venn centers or the Chern number. So I was just wondering if one can use the idea of something like called Dresd bands. So we could somehow use the same idea like in the quantum case where we have this Fermi liquid theory. So we define interaction with something like non-interacting physics. So here, maybe in the weaker case, we could try some like Dresd bands, and where this explanation could be done. It's just a naive guess. I'm not sure if how. So
yeah. You're talking basically about getting an effectively interacting band structure. So getting a new band structure that incorporates the interactions, right? We didn't do exactly that, but we did something similar, which is that I know, Alberto, you're looking at the clock, so I'll be quick. We did something similar, which is it's a kind of a posteriori calculation. It has 0 predictive power, but at least it gives you some formalism. So what you do is you take the soliton, you look at the potential that it generates, and then you think of that as a broader pump model. And then you calculate the bands for that. You expand the unit cell, and then you calculate the bands associated with that model with the new potential.
I see.
And, of course, just by construction, you get the Chern number corresponding to how much you pump the soliton. But, it's a formalism thing. It's kind of, in a way, we were debating whether to include it or not, because in the manuscript, because, it doesn't tell you anything new. It's something that, okay, if you want to do formal calculations, you can use that, I guess. So.
Okay, I see. Thanks.
Okay, thank you very much, Mikael, and thank you to all the speakers. It was a very nice session. I liked it very much. Well, I like the whole conference. I'm liking it very much. So if you want to keep on and learn more things and exchange more, get some more exchanges at 4:30, we are back with the last session of the day. Okay, see you later.
We can start. Welcome everybody to the last session of the day. We have 4 great speakers. I'm really looking forward to their talks, and we start with Mohammad Hafezi, and he's going to take a talk about the interplay between electronic and photonic topology.
Thanks, Anna, for the introduction and also the invitation and putting together this nice online workshop. I hope this is the last online workshop and that the rest will be in person. So the topic of the workshop is topology and quantum optics. So this work is kind of combined both of them. The first one is actually closer to the last talk that have to admit people, or someone will. I can admit them. Yeah.
Just continue and ignore that.
Okay, so you take care of the admission. I'm the co-host only. So the first talk is actually in a good position because the previous talk by Mick, he gave a very nice introduction on the role of nonlinearity in topological photonics. So that would be the first part of the talk. And then the second part of the talk would be this coherent interaction between light with orbital angular momentum and electrons. Basically, we have an electronic system that has some topological behavior, and we have some light that has some topological property. What's the interplay between them? In particular, can we use light to probe and manipulate topological electronic states? So these are based on these 3 preprints, and one of them is coming soon on the archive, and there will be a bunch of posters that I would refer to, and they're all theoretical works so far. So what is a frequency cone? Just as a quick introduction, is like a ruler for time and frequency. The ruler is for space, this is for time and frequency. It is composed of equidistant peaks in the frequency, and then you take the Fourier transform that will translate into peaks that are separated with equal distance in time. The way that we usually do it is that we have a non-Rayleigh material. You pump it with the CW laser with a single frequency, and then what comes out in certain conditions is that there is an interest in the community to make them miniaturized, make them as small as possible using micro-ring resonators, either in silicon or silicon nitride or other material, and really going to the tens of microns limit. There is a nice review by Kippenberg and company where they review the progress when you have a single ring, you pump it strong, and then you generate this frequency cone. These are these peaks that are equidistant, as shown over here, over an octave, more than an octave. So the challenges is that one would want to increase the efficiency, meaning for the given power, you want to have as much frequency cone generated as possible. The other problem is the lack of tunability. Once you have a single ring, you just basically have a single parameter that you can play with, meaning that the optical path is a single parameter, so that determines your loss, that determines the distance between these guys, the teeth. You cannot, for example, have an extra feature over here, and those are useful. So potential solutions are making arrays of ring resonators, so not just have one, but like arrays of them, 2, 3, or one-dimensional, two-dimensional. So that there are some ongoing works in particular in Kippenberg's group. And then also pulse the scheme, how you can pulse the system not with just a CW, but in interesting things, pulse the schemes to increase your efficiency. So now the subject of this work is that can topology play an effective role? So in order to set the stage, how these frequency cones are generated in micro-ring resonators, we look at the single ring where we have a four-way mixing process. So we start with spontaneous four-way mixing, we pump it, and then you pump it at some certain frequency. Because of the four-way mixing process, you have this Hamiltonian that basically describes the destruction of two photons, annihilation of two photons, and creation of two other photons at higher and lower frequencies, such that your energy is conserved. So in another way to say it is that you have two coming photons and then two outgoing photons. And of course, the Hermitian conjugate will be the opposite of this process. And at the same time, you have to satisfy the conservation of momentum or phase matching, as we call it in optics. And of course, this can go on. This can be the first order, second order, etc. So you just basically create this nice pattern. And then that's followed by stimulated four-way mixing, meaning that now that I have one peak over here, this guy can emit into this mode and then to this mode that is already occupied. And then after some time, you have this very nice cone. Now, this is brought to us by this self-enforced balance between the gain that I just described, and the dispersion in the resonator. We usually don't with the linear dispersion. We have group velocity dispersion, and that's kind of needed to counterbalance the effective gain. Once you put some intensity, once you have some gains, you put some intensity in some mode, that mode starts to shift forward or backward depending on the amount of light that you've put in. And that has to be compensated by dispersion. So when we are talking about this frequency cone, these are actually very specific solutions that happens where in a regime you have this gain and dispersion balance such that we have generated this nice cone. That's not always the case. So now what is important over here, I'll mention that how that's possible, is that this phase matching, and we hope that this phase matching would be improved by the role of topology, as I explained in a second. So how the optical frequency cones are generated, as I said, they are not always generated when you pump a single ring resonator. In particular, if I look at the intra pump power, you pump the system with some frequency delta omega p, and then you look at the intensity of light inside the resonator, we have some pattern like this. This is numerical simulation. So you're pumping it detuned with respect to some central frequency, and then you see something like this. A better way to visualize the system is that you have a specific round trip. So basically your photons are going around this resonator with a specific round trip C over L, C being the speed of light and the material, and L will be the length of the system. So this tau r, this tau round trip, tells you that after each tau r, your pulses are coming back to the same place. So if I take a snapshot and then see the pulse that it's somewhere over here and somewhere over here, I can tell what's going to happen after TR. This is just periodic with TR. In particular, if I take a snapshot and I see my pulse is over here, then after time TR, it will be again at the same position. So as I said, as a function of omega p, you can have different regimes of interest. So for a fixed input intensity, this is some numerical result for a specific input intensity. When you sweep the frequency of the pump, you go to different regimes. Once it's a soliton, that you have a single peak that is traveling around this resonator. So this is your pump frequency, and these are other orders. So mu is the number of modes. So this is mode number mu, mu plus 1, mu plus 2, mu minus 1, etc. Now a good comb would be something that is smooth, and you have mu 1, mu 2, 3, 4, etc. And of course, you have this guy that it's the pump that you have put, of course, that would have a higher intensity. If you move your frequency to another regime, then you will go to a chaotic system. And then if you move further, you go to this so-called Turing rolls, where you don't have a single peak, you have multiple peaks. So in time, you will have this situation, and in frequency, you would have this distance. So you're basically losing some teeth in your frequency. From here, you have all of them for all positive integers. Here, they're missing for every 12. You only have a tooth on every 12 mode. Now, as I said, when you pump the system, ideally you want the pump to be completely absorbed and then and generate combs, not just come out of the system as it was before. So you want this peak to basically disappear and all be very smooth comb, but that's not the case. And for a single ring, you have this fundamental problem that you usually have this efficiency less than 5%. So that might be another problem that we might be able to address with our topological system. So the topological system that we are using is this single, this is coupled ring resonators that our group and other groups have been using for various reasons to show quantum Hall properties, lasers, reconfigurability, and then more recently, that is more relevant to this talk, is the generation of pairs of photons. Either you pump it on one frequency and then you generate signal on either at two different frequencies, higher and lower, or you pump it in an inverse way. You pump it on this side and then this side, and you want to generate photons in the same mode to make photons indistinguishable. And these were all possible by basically this robust phase matching that topology brought us. So we are just looking at the same system. In the quantum regime, we were just generating single photons or pairs of photons. Here, we are not in the quantum regime. We are just looking at the non-linearity effect. So this idea that we would like to explore, this topological frequency comb in general, but specifically we focus on a model that gives us the topological edge states in the linear regime. So in the linear regime, we have some generic tunneling, nearest neighbor, next nearest neighbor, and some on-site staggered potential. This was shown that you can have these edge states, which call them super rings, because now this ring mode is constructed with many of these modes. And then if you come in the central frequency around the edge mode, you pump the system. If you're in the edge, most of your power would be on the edge states. If your frequency is resonant with the bulk, of course, most of the power would be in the bulk. So the power in the super ring will be small. We would like to be in this regime. We would like to pump the system in this regime. This is similar to this synthetic dimension that a lot of actually maybe people on this call have looked into. Sean-Hui Fan's group, Jacopo Carusuto, Hannah Price, and Tomoki and company. So this is exactly the same. So now this Hamiltonian can be written for the central frequency, central mode, and +1, -1, etc. So you have a series of that. So if you look at the linear regime, that's the frequency, and the power in the edge mode would be something like that. That would repeat itself after each free spectral range. So you have this spectrum that appears after each free spectral range. Now, if you compare it with a single ring that just had a single mode in each of these free spectral ranges, now you have a bunch of modes. Because we are using many cavities around many resonators around the edge of the system. So that's basically the difference. Now this difference becomes important because now we have two energy scale in the system, or two time scale in the system. One is the free spectral range that is given by the size of individual ring, and the other one would be the slow frequency, which is related to the perimeter of the system. Now, using this separation of time and energy, one can actually solve this problem numerically. Otherwise, it's really hard. So the idea is kind of simple, but to get it work is really hard. And this is thanks to Sunil, who did it during COVID when the lab was closed. So it's not a trivial problem. So what we would expect is that in a single ring resonator, you would just have this linear spectrum. And then if you pump it hard enough in a specific regime, you will generate frequency comb. Now in the topological system, you have this spectrum in the linear regime. And then when you pump it, you expect that you generate these combs like this. So now again, what we are expecting is some self-organization of solitons that again would be a balance between dispersion and gain. So just as a reminder, here in a single ring, as I mentioned, you sweep the frequency of the incoming pulse, incoming pump. Your intensity changes like this, and then you get these patterns: the chaotic, Turing rolls, and the solitons. You just have one mode, one pulse over the round trip time. Now, in this two-dimensional topological system, you would see a similar diagram as the function of pump frequency. Again, this will be the round trip time. And now, instead of integrating over we only had one ring over here. Here we had many rings, but we don't care about the rings on the bulk. We only look at the intensity of the rings on the edge. So that's the quantity that we are looking at. You sweep the frequency, and then you look at different regimes. In particular, when we are in this regime, similar to the single ring, we have the solitons. So you would have now this soliton, that it's not just the one soliton that it's rotating around the single ring, but it's actually a nested soliton. So you will have each ring that is embedded in a bigger ring, and then it forms a perfect soliton and it goes around the system. It's a very beautiful animation by Sunil. So now if I look at the output spectrum, you see the generation of the frequency comb. You will have two energy scales, as I said, fast and slow, and that's it. Basically, you have your frequency comb. Now, you can go to other regimes that you don't have just one peak going around the system, but now two solitons that are going around the edge of the system. So that would correspond to this frequency, omega 4p. And now these are topological, meaning in the sense that if I put some disorder in the system, they would go around it. And unfortunately, I couldn't make the animation work. So these are 3 snapshots. So the pulse comes in. There is one site that it's missing, and instead of getting back scattered or go into the bulk, you see that it nicely goes around the impurity and continues its way. So these are all numerical simulation that works out very nicely. One can also look at some phase diagram for this system as a function of pump power and the frequency of the pump. You can go to different regimes. You can go to this chaotic regime, Turing rolls, and this super solitons that I just described. So this was a topology-enabled self-organization of soliton that we realized theoretically. The good thing about this is that it has an order of magnitude higher mode efficiency compared to a single ring. As I said, in a single ring it was less than 5%, but in these systems it can be actually higher than that. We don't know a theoretical limit for a topological system, so that's kind of like an open question. Actually, a more general open question is that, do we have a phenomenological theory to understand these topological solitons? This was actually a question in the last session as well, that we have this strongly nonlinear system. Do we have an effective theory that is agnostic to the microscopic model? So here we used kind of like a Haldane model with optical nonlinearity. But what if I choose like a Hofstadter model with nonlinearity? What if I do a SSH model with nonlinearity? Do I have a phenomenological theory like, I don't want to make a close connection to quantum regime of Chern-Simon theory, but something like that. That would be phenomenological. It does not depend on the details of the system. It just have topology and nonlinearity. I think that's an open question. And another one is that what actually gives rise to this robust topological edge states? Is it just purely phase matching that we inherit from the linear domain, or no, there is some intrinsic nonlinear effects that are coming and how they play with each other? So as I said, this work was really led by Sunil, who did all this nice work, and it was in particular in a collaboration between our colleagues at Maryland, because we didn't have any expertise in frequency comb, and we learned a lot during this project. So we were very fortunate to collaborate with our colleagues on that front. So I have 10 minutes left. I just want to advertise a poster by my student Chris Flower. It's not really quantum optics or nonlinear. It's actually a very simple idea. Can we again use topology for something useful? And that's the idea of making a taper. And if you're interested, you should go to his poster. The idea is that can we make a taper in a system using these topological systems, because they are robust to backscattering. And he has showed that we can actually squeeze the mode, convert the mode from a wide region to a small region very, very efficiently. So now in the very few minutes that I've left, I would like to talk a little bit about the interplay between electrons and topological states of light. The idea is to how we can use optical probing or manipulation of quantum Hall states. Usually in electronic system, you use transport that are coherent but global, or you do STM or SED that are local but non-coherent. The idea is that whether we can use light to these states and manipulate them. Since I don't have time, and some of you have heard me talking about the basics of it, and you're all experts in quantum Hall physics, I skipped the preliminaries. Basically, you have a two-dimensional electron gas, and then you have quantum Hall states, and they're optically active. What we realized with Michael Gullens a while ago is that these selection rules are actually dramatically modified. You think that you always in a dipole approximation limit, and you only have dipole emission and absorption pattern, but it's not the case. In particular, in these quantum Hall systems, apart from these localized states, you have these edge states that are very large, and they can be larger than the wavelength of light. So usually we are in the dipole regime, that your wavelength of light is much larger than the extent of your atomic orbital. But in these systems, that can be violated. So in principle, you can go from a one Landau level, say Landau level 0 and orbital m, to, in the symmetric gauge, to Landau level 1 with the orbital angular momentum m prime, with some light matter interaction in between. So this is the Landau orbital in the symmetric gauge, and then this is the Landau orbital in the symmetric gauge. And then in principle, usually you think that this should be just R, but in principle it can be non-zero for other values. In particular, in the photoluminescence, you expect that you can absorb the light and come back in the same position in the dipole limit, but you can also emit light with non-zero orbital angular momentum. This is really hard to observe in the experiment. So now alternatively, Ben has been, with Tobias, has been thinking about other ways to see this effect. And the idea is very okay, missing one slide, so I'm gonna just explain it over here. The idea is basically an optical incoherent Laughlin pump, that your light has some orbital angular momentum. So this will be absorbed coherently with your electron, so it will increase its radius. So it will go to the upper limit with some non-orbital angular momentum, and then it spontaneously decays. But that spontaneous decay would not would be democratic. It would not add or subtract any orbital angular momentum on average. So it's like a fountain. You push the photons to higher radius if your orbital angular momentum has the right sign, and then they come down democratically into the ground state. And if you keep doing it in this simulation, you see that if you resonantly derive Landau level 0 and 1, then your states will be pushed to the edge. And depending on the order of angular momentum, you can have the radius of your electrons increase or decrease depending on the sign. And one curious thing is that if you now look at the photocurrent scaling will not be linear in power, but would have this weird scaling with the power, or here this is the Rabi frequency. So if we want to learn more, there is a poster by Ben, and now the open question is that can we have an experimental verification of it? And more theoretical question is that could this be a more general approach to create and measure spatial electronic coherence? So here we use the fact that we have quantum Hall states, we know their Landau levels, in symmetric gate we write them, everything like that. But then it might be more general. It doesn't have to be a quantum Hall system. It can be any system that the electronic wave functions are extended. So whether these techniques can be used or not, this is an open question. So Ania has raised his hand, so I'm out of time. There is another related
You still have 5 minutes.
Yeah, sure. I just wrap up actually. That's kind of my last or penultimate slide. That was in the quantum Hall regime in graphene. Similar effects can be seen, or interesting effects can be seen in a semiconductor when it's driven by some light that has orbital angular momentum. Imagine that you have a valence band and a conduction band, and you drive your system with some light that holds orbital angular momentum. Now this is a semiconductor in contrast to the to graphene in the last section. And then we know from these nice works that we have the Floquet topological insulator created. So you can invert the band, etc. But now since the light has this non-zero orbital angular momentum, which can be described by this simple Hamiltonian, then you will not only get the edge states usually on the system, depending on the polarization, if it's sigma plus or sigma minus, but also you will get these states in the bulk, even if you don't have sigma plus and sigma minus polarization. In particular, depending on the order of your orbital angular momentum of light, you will have the same number of branches that appear in the bulk. And these are like vortex states, this is a typo, that appear in superconducting, the conducts of superconducting material. So one can actually now create these vortices, and the size of these vortices, their number, etc., depends on the parameters of your light. In some regimes, they're linear, so they're just like a harmonic ladder. In some regimes, when you squeeze it, when you have a light that is small, then you will get some anharmonic ladder. And we've been thinking maybe if it's anharmonic, maybe you can actually manipulate it like a quantum state. So with that, so again, as I said, there is a poster by Iman. If you're interested, you should feel free to stop by his poster. And with that, I would like to stop over here. Thank you very much for your attention.
Oh, thank you very much for this nice talk. So please ask questions, raise your hand. I see here Lavi Pretty. I will I can unmute you, right? So.
Yeah. Hi. Thanks for the nice talk. So Mohammed, I had a very naive question. So at one slide you were showing like this control of these nested solitons. So at one case they were only localized at one edge. In other case they were localized at two edges. So I was just wondering, is this controlled by this omega p, like the omega p you were talking about in the beginning?
Yeah. So that's basically, yeah, you're right. So we have this omega p over here. Depending on that, we go to different regimes. You can have either one of them or two of them, and then you see that it's over here.
Yeah, and one other, let's say, two quick questions. So in one regime, you showed actually one could even, I don't know, study some chaotic in these systems, like for some omega p. So, I mean, they could be reliable systems. I mean, I was just wondering to study some chaotic dynamics.
That's beyond my expertise.
Okay.
Maybe. Yes, so this even in a single ring you have chaotic dynamics, and then in the multiple rings, you would also have this chaotic dynamics. So this chaotic region over here. And it's very rich. I have to say, these nonlinear systems are super rich, and you really have to know what you're looking for. And even if you know, it's really hard to find them. So Sunil did a heroic job to find the right parameter regime that these things can work. So in principle, it's like a forest. I don't have enough expertise in nonlinear chaos theory. So if you're interested and have some specific questions about the system, I would be happy to chat afterwards.
Okay, so yeah, the last one just was like you were talking more about this phase matching. So is this I am not yet anywhere like much expert in this, so I just wanted to know a bit more. Sorry, there's so much noise.
No
so yeah, so could you say something about this phase matching? Thanks.
So imagine that let's think that I want to create two photons. Okay, this is simpler. So I have this nonlinear Hamiltonian, right? It kills two photons and then creates two photons, right? Now, in order this process to be efficient, it should satisfy energy and momentum conservation. We good? So now look at this system. So now I pump the system, then the pump is circulating in the edge of the system. It's like a linear waveguide. Now this linear waveguide, because of nonlinearity, it can break into two photons, the signal and idler. Now the momentum of the signal and idler should be equal to twice the momentum of the circulating pump. If that is not the case, then this process is not efficient. For example, if you have some disorder in the system, then K is not even well defined. So your block wave is no longer a good quantum number. And then you don't get anything. If you take a one-dimensional array of ring resonators, you get Anderson localization, and you cannot do phase matching at all. So these topological systems allow you to get around that localization problem, and then have these waveguides that have a well-defined momentum. And then as long as there is a possibility to match these momenta to each other, you get an efficient process. I hope that makes it a little bit more clear.
Okay, thank you. We're already out of time. There are still 3 more questions. I would ask Daniel, Alejandro, and Clivia to ask these questions in the chat, and Mohammed, it would be great if you can then answer them in the chat.
Sure.
Thank you very much for this nice talk, and then we're ready for our next speaker, Lorenza Viole. Is going to give a talk about analogous of Majorana fermions and metastable driven dissipative bosonic systems, right? Okay, great.
Yep.
So you have the stage. Looking forward to it.
So can you see my screen fine, and also my mouse?
Yes.
Perfect. So I actually would like to start with a warm thank you for having me in this workshop. I actually have very fond memories of other meetings in Binasca. So, I mean, even just be there virtually, it's a pleasure. And I like to say that I am particularly excited to have the opportunity to share with this audience some of the recent work I've been doing. This is work that has involved my former postdoc, Emilio Cubanera, is now a faculty at SUNY Poly, and my graduate student, Vincent Flynn, who is here in the audience. And I would like to make sure that I give him right away a ton of credit for the results that I'm going to share with you. Okay, so given this audience and given all that we have heard about topology, I will not spend much or no time at all justifying why obtaining a full understanding of the roles, the manifestations of topology across quantum phases of matter. This is where I have approached the topic, but also light is a very important endeavor, both from the fundamental and the practical point of view. Rather, I would like to just go to what, if my mouse permits that. Hello, it's frozen. I'm sorry, doesn't want to. What should I do? Let's see. Help. Huh. Okay. I don't know what happened, but here we are. I wanted to just go to what has constituted the starting point for our work, which are symmetry-protected topological SPT for short phases of electronic matter. So let me make precise what I mean by this. These are phases of matter, like I said, fermionic matter, which are well described by non-interacting, so mean field Hamiltonians, which generally will be particle non-conserving. They're going to be fully gapped and stable, by which I mean, as usual, perhaps bounded from below. So we know by now that all of these systems in equilibrium, they have been fully topologically classified. We have a famous tenfold way. And perhaps one of the most remarkable, implications that this classification is giving us has been the bulk boundary correspondence, which provides us with the relationship between topological bulk invariance and the number and properties of boundary localized edge modes, which are topologically protected. And since I had Majorana in my title, well, I mean, be prepared to hear about, in particular, these protected modes that I am referring to from bulk boundary in fermionic matter. They were the one in topological superconductors. So, suppose we follow an exactly analogous line of reasoning for free boson and ask, are there equivalent results for free non-interacting Hamiltonians of bosons, which are fully gapped and also are stable? Are there topologically mandated bosonic zero modes? And we actually wanted to get a kind of precise answer to these questions. And it is possible to do so. Basically, the kind of bosonic Hamiltonians that we are facing are described by quadratic Hamiltonian in some, canonical creation and annihilation bosonic operators. And it is possible to give precise answers, but I don't know, maybe you're not going to be surprised at all, but they are also kind of disappointing in the sense that these answers come in a series of no-go theorems. I have listed them here. The details are in this paper, but let me just call attention in particular to the fact that if we insist in requiring the analog that we had for fermions for bosonic Hamiltonians, well, it is impossible to have non-trivial symmetry-protected topological phases. Basically, all Hamiltonians are going to be adiabatically connected with one another, and it is impossible to have, localized zero modes. Zero is not in the spectrum when we consider open boundary conditions for the systems. And if we wonder why that's the case, the obstruction to that in all cases come from essentially the stability, the thermodynamical stability constraint, which for the bosonic case turns out to imply a gap condition that has no counterpart for fermions. I don't want to imply that, other manifestations of topology which are highly non-trivial cannot be found in Hamiltonians if we relax some of the requirements that I have alluded to. In particular, it is possible to go to strongly interacting regime. It is possible to allow for gapless phases, or it is possible to consider instabilities. And in all these cases, there are some of the works that I mentioned here. There are non-trivial topological manifestations that come up. Does this perhaps exhaust all the possibilities if one insists in looking for Majorana physics? Well, the answer is, it goes backward. interesting. The answer clearly is no. There are a lot of topological phenomena that are being increasingly characterized away from equilibrium in the context of open quantum dynamics. And this can happen at both the semi-classical level, where the dynamics is described by non-Hermitian effective Hamiltonian, and we have heard a lot about this in the talk by Flor. But I am going to be most interested in a fully quantum regime, in particular Markovian dynamics, in which case the description happens via Lindblad or perhaps an input-output formalism. I think, as far as I am concerned, I was particularly inspired by this work almost a decade ago on using engineered dissipation to induce topology in the steady state. But then there's been a lot of work coming along, and in particular, these two beautiful works by people here in the audience. They have pointed out a very interesting relationship between bulk topology and a particular kind of directional amplification. So with that, let me, however, go back to reformulation of the original questions I posed. So the questions are there equivalent of SPT phases for non-interacting, but now dissipative bosonic systems? And still, can we find topologically mandated analogs of Majorana fermions? So like I said a moment ago, my focus is going to be to Markovian dynamics described by a Lindblad master equation, and the non-interacting nature will be reflected in the fact that we consider quadratic Lindbladians. Now, since I'm pretty sure I might not be able to tell you everything that I would like to, let me just highlight already the main upshot, the main message that is going to come is that, in some sense, to look for the answer for these questions, what we think is necessary is to shift the focus from the steady state to the transient behavior of the system. And that is going to be the essence of what we call metastability for quadratic bosonic Lindbladians. I also want to call attention that full details of what I'm going to talk about are available in this preprint. And Vincent is going to present a companion poster that will highlight some of the many aspects. I will not have the time to go into it. So let's see how far we can go. I'm sorry about this, it's a dense math slide, but I need to set up the stage for the type of dynamical system we are going to consider. These are going quadratic, bosonic, Lindbladian on an n-mode bosonic Fock space. We are going to have a Lindblad master equation. However, I will mostly think in terms of the Heisenberg representation for observables in terms of the dual Lindbladian. And the equation of motion that we obtain for the observable, given the Markovian model we have, they can be written, for instance, in terms of this GKS matrix, which is positive semi-definite. I want to call attention in particular to the fact that arbitrary linear observable, so observable which are linear in the canonical creation and annihilation operators, they are completely determined by a certain matrix that we call the dynamical matrix, and has this particular form. It turns out that this matrix plays a very important role in determining both stability and spectral properties of the problem. So what I mean by this, let me recall, this is a dynamical system. It's a linear one. The quadratic boson, from the point of view of the differential equation that we have, this is going to be dynamically stable if expectation values of arbitrary observable in any initial condition will remain bounded in time. And I'm going to assume that the matrix G here is going to be diagonalizable, in which case one can show that the Lindbladian is diagonalizable as well. It has a spectrum, and the spectrum of L can be obtained from what is called the rapidity spectrum, which is the eigenvalues, as you see, of this minus IG. Now, a sufficient condition for dynamical stability is that this minus Ig is what we call a Hurwitz matrix. And that means that the possible eigenvalues for minus Ig, they have to be confined strictly to the left of the complex half plane. So the real part have to be strictly less than 0. In that case, the dynamics of the system, and this is very important, the dynamics of the system that we are going to consider, they are going to converge to a unique Gaussian steady state. Okay, the convergence to this steady state is happening exponentially. This is true because we have, like I said before, a linear system, and a quantity which is very important for having Markovian semigroup is the mixing time, which essentially gives us an upper bound for how long it takes for arbitrary initial state to converge to the steady state, and a quantity that enters in the mixing time and is well known in the field is also the spectral gap of the Lindbladian. All right, so with this, yes, there is something that doesn't work with my presentation clearly. Don't understand why this is happening. My apologies. So with this, I will focus more specifically on quadratic bosonic Lindbladian, which describe one-dimensional lattice systems that have translational invariance up to boundary conditions. This helps a lot in terms of the analysis because this dynamical matrix acquires nice mathematical structure, like it becomes a block Toeplitz matrix. If we have open boundary conditions, it becomes block circulant if we have periodic boundary conditions. And it gives us the possibility to obtain even analytical results in some limiting cases. To make things even more concrete, let me pick as an illustrative setting a system which was introduced by Ash-Clerk a couple of years ago, and we call now the bosonic Kitaev chain because it has a very nice duality to the fermionic Kitaev chain that is very well known in the field. The basic Hamiltonian is given here. We have essentially a system with number conserving term which describe hopping within sites, and then we allow for number non-conserving terms through both like a parametric driving term and mu. When present, you can think it could describe a non-degenerate parametric amplification term. Point that I want to make about this Hamiltonian is that thermodynamic stability is lost. And what we are going to do is to construct two dissipative models, two quadratic bosonic Lindbladians that only differ in their dissipation. So the first model consists basically, imagine that we take these and add uniform on-site dissipation to this bosonic Kitaev chain, and we look at what I called before the rapidity spectrum of the system under both periodic and open boundary condition. Now, you have different curves here. There are two different parameters, ratios of the dissipation to these delta parameters, and the ones that I'm showing him where I am pointing to ellipses, you should think about having the system under periodic boundary conditions, whereas when you see like segments, this corresponds to open boundary condition. So what these results show is that for certain parameter regimes, changing from periodic to open or vice versa does not change the dynamical stability properties of the system. We are confined with negative real eigenvalues, as you can see, whereas for other parameters in the system, if we, for instance, in this case, change the boundary conditions from open to close, what happens is that the rapidity spectrum crosses over into the positive real parts, and so the system becomes dynamically unstable. Now, there is this dramatic response to boundary conditions. In the other model that I'm going to consider, what happens physically is that the model is the same that we had before with uniform on-site dissipation, but also now next nearest neighbor one is added to the one that we had before. So there is an additional term with a certain strength. And again, the rapidity spectrum is shown here. Open is red, closed is periodic boundary condition, the black. Again, dramatic response to boundary condition. These plots, they look, so this is a common feature between these two models. There is a seemingly minor, but actually very important difference. And the difference is that the rapidity spectrum under periodic boundary conditions of the model 2 that we have does not wind around the origin. So if we want to capture a little bit more precisely, here are the two models again side by side. If we want to capture the behavior, the dynamical behavior we have seen a little bit more precisely, I think we need to refine the stability notions we have. And here is what we are going to say. We are going to say that if a quadratic bosonic Lindbladian is dynamically stable for open boundary conditions, but becomes unstable, dynamically unstable when we look at periodic, then we say that the open boundary condition system is actually metastable. Metastability is a very well-known phenomenon. It is typically associated to a multiplicity of relaxation timescales, and you will see why we use this terminology in a second. So in contrast, a quadratic bosonic Lindbladian like this one here, which remains stable for both open and periodic, we refer to it as being unconditionally stable. Now, capturing properly the beta stable behavior is mathematically requiring a different tool than just the eigenvalue, the spectrum. We have to turn to something which is a little bit more sophisticated, but very well known in the applied math literature, which is pseudospectral properties of the metric G. And the reason for that is that this G is not normal and the spectrum is very fragile. In contrast, the pseudospectrum, you should think about it as almost eigenvectors or eigenvectors up to an epsilon correction, turns out to have nice robustness properties, for instance, against changes in perturbation that can happen. The very important takeaway message that I want you to get from these slides is that what happens for these systems is that unstable behavior, dynamically unstable behavior can happen in the thermodynamic limit, even though the system remains dynamically stable for arbitrary finite system size. And it turns out that this unstable thermodynamic limit imprints itself in a lot of interesting properties in the relaxation dynamics. In particular, we can show that the mixing time, so the time it takes for the system to approach the true steady state, that which I said is unique and is Gaussian, is actually exponentially divergent, is diverging with the system size, is diverging linearly with the system size. I said exponentially, delete that. This is a linear divergence with the system size. And this is also interesting because, for instance, in the model system, we consider the spectral gap doesn't close, it remains constant. Something also that happens when metastability sets in is that transient amplification and directional amplification is possible. This has been discussed at length in the papers that I was mentioning before. As far as our model is concerned, these plots, for instance, show the behavior of the expectation value in time of the position operator at one of the boundaries, the nth boundaries. And what you see here are the model 1 and model 2 in what we have called the unconditionally stable. So there is basically this this what corresponds here is like, I think is like 500 different initial conditions that are used. And what you can see in the metastable regime is that the peak, the location in time at which the peak of the position happens grows, as you can see, beautifully linearly with the system size of the system. So, okay, time to go back in my remaining time to the original questions that I posed. The questions are still up here. And I have repeated a couple of times that the steady state for our system is unique, is Gaussian, but it can also be hard to reach in terms of the time it takes to approach it. So let me look instead at the transient regime to see whether, remember our goal was to see for equivalent of SPT phases in terms of looking for Majorana-like types of physics. So a hint for that comes already in the bosonic Kitaev chain, because it is possible to see, even analytically in certain parameter regime, that there exist approximate zero modes, which are given by these, operators here that I wrote down in terms of these parameters. But unfortunately, what happens for the bosonic Kitaev chain is that these Hermitian, exponentially localized and nearly conserved quantity, this commute nearly with the Hamiltonian of the system, they exist only when the system is at the cusp of instability. Now we can try to circumvent this instability by adding dissipation, which is what model 1 does. And in model 1, it is possible to again, in some regime, compute analytically the existence of some approximately conserved up to, this is the approximate conserved means that these operators obey a relationship of this form, and when this delta parameters is rightly chosen, you see that this is going to give us exponentially small correction. So we have again Hermitian, exponentially localized and nearly conserved operators, and it is very important to note that these exist precisely when the rapidity bands of the system under periodic condition, they wind around zero, and I see Anya's hand. However, the problem we are having here is that in general, we would like to combine these quasi-particle operators into kind of like a real and imaginary part of a split boson, right? It's not possible to do that with these operators as they are, because they don't obey the right commutation rule, they don't have the right algebra, they are not in general canonically conjugated to one another. So our proposal is that instead, bosonic analog of Majorana fermions, well, to get them, we need to bring in two other operators which carry a superscript S, because they are attached to symmetry generators. And our proposal is that these bosonic analogs of Majorana fermions are pairs, left and right, of conserved quantities and symmetry generators, which are identified in the Hamiltonian scenarios, but in general split when we have an open quantum system, because the Noether's theorem essentially is broken. So we have, in this case, we can restore the correct algebraic commutation relation we expect for Majorana kind of quasi-particles here. And let me also, let me repeat this, the presence of these Majorana bosons is what we call topological metastability. Metastability is one key ingredient, is necessary, but is not enough. What is necessary to also have for topological metastability is that the winding number of the bulk rapidity spectrum at zero is non-vanishing. And when this happens, like I said before, each conserved Majorana boson on one edge can be paired in general with a distinct symmetry generator, which is localized on the opposite edge. I know that I don't have much time to go into details here, but let me call attention to what is the topological phase diagram of the system that we have considered. It's a phase diagram that again carries Majorana bosons in the region where we have topological metastability, in the region where the language, the mathematical condition to say these rapidity bands winds around zero means that zero belongs actually to the pseudo spectrum of our dynamical matrix, with epsilon being exponentially more small in n. I want to stress these Majorana bosons share another key properties with their fermionic counterpart, which is robustness against perturbations, which they get because the pseudo spectrum is robust. The existence of Majorana bosons, which is one of the distinctive features of topological metastability, also goes hand in hand with other properties that one sees in more like a topologically sourced manifold of quasi-steady states. And I really would like to call attention to Vincent's poster for that. I will use just 2 more minutes to say that, of course, one would like to wonder, can we see these creatures, these Majorana bosons, if they truly exist? And what we have been thinking in analogy to fermions is like to look into like signatures, for instance, in 2-time correlation functions of observables, looking at their spectra. And what you see in this last picture that I want to show you is a normalized spectra for the correlation in the steady state for the position in the lattice size n. And what you see is that when the system is unconditionally stable, there is no peak at zero frequency. There is a peak when it is metastable, and this peak grows, we conjecture, with a particular dependence upon system size. With this, I will just, I think, put up my slides with the summary. Of course, there are a ton of questions that we need to investigate more carefully, but I think I would prefer to stop here and apologize for the extra time and give back things to you and Ania.
Great, thank you very much. I think we have we don't have much time, but we perhaps for one question. I'm seeing a question by Clara, so I'm just reading it. Or do you want to ask it? It's perhaps faster, Clara. Okay, perhaps not. I can't unmute. Okay, wait.
Well, I see a lot of them in the chat. I will definitely try.
Yeah, I think now it works.
It works now. And Dr. Clara, please ask.
I couldn't unmute before, sorry. Yeah, so I have 2 questions, but I hope they're related and brief. So the first is, I suppose the exponentially long pre-thermalization times you showed is because of these exponentially small eigenvalues that arise when the winding number is non-zero. Is this correct?
I would be careful to say exponentially small. I don't want to give the idea that there is, like in other mechanisms for metastability, Markovian open quantum system, there has to be a separation between groups of eigenvalues in the Liouvillean. Yeah. I'm not sure this is the case, or it does have to happen. What has to happen in our case is that the rapidity bands of the system under periodic boundary condition, they don't wind around the zero.
Okay, yeah, I was just trying to understand the different time scales and if they're related somehow to eigenvalues, or maybe singular values are more suitable.
Okay.
If they expect, but
I see what you mean. I think pseudo spectrum is really proper tool also because in dynamical systems, like it is the one that is used to capture the transient behavior as opposed to the steady state. But I don't know, probably there are connections to singular values that for G.
Yeah, and the second question is maybe related. So under open boundary conditions, the system can be either unstable or stable. So would you, I suppose, do you still observe the metastability in both cases? I suppose not, right? Because if the system is unstable, then I suppose it will diverge immediately and you can't see. Because what we saw when we just calculated the dynamics of these systems in this direction amplification paper was that there was an unstable regime and a stable regime and an unstable.
Right.
So I was just
no, it
wondering,
depends on the parameter regime. For instance, in model 1, there are parameter regime which corresponds to the unconditionally unstable case where whether you have open or periodic doesn't affect the stability property.
Okay.
So that's the conditionally unstable case. So,
okay.
Thank you.
Great.
You're very welcome. I will look at the chat and I think I will be busy responding and yeah.
Please, if you have more questions, put them in the chat. Lorenza, thank you very much for this great talk. I have something to read.
Sorry about the glitches of the sharing. There were some issues. So.
Oh, that's no problem. So these things happen.
Yeah.
It all went fine. So with this, you can now okay. And the topic of the talk is unconventional quantum optics and topological waveguide QED. You can start.
Can you hear me?
Yes, now we can hear you.
Now you can hear me. Okay. So thank you to the organizers for allowing me to talk here today and for this very interesting program that they have put up. So the main question that we wanted to answer with this work is whether there is some effect of topology in these hybrid systems in which one has quantum emitters coupled to a photonic system, right? So if one has a topological photonic system, is the topology affecting the quantum emitter dynamics, for example? And the answer is yes. And we predicted several phenomena that has been shown experimentally very recently. And I think the next speaker will also talk about it. So I will focus just on the theory side of it. Right. So this is a schematic picture of the system that we have studied. Of course, the question is very broad, so we had to focus on a particular model, and we chose the SSH model for the photonic system, which is represented here with these harmonic potentials. So you all know what is the SSH model. I think I shouldn't explain to you any details about it, but just let me quickly recap. It is a one-dimensional topological insulator. Here we have the bosonic version of it, and it consists of two sublattices that are connected with alternating hopping amplitudes. So here, for example, you can see that we consider hopping between the bosons inside the same unit cell parameterized with this delta parameter. And when delta is positive, the intracell hopping is larger than the intercell hopping, right? And as you know, depending on the ratio of these two hoppings, the system can have a non-trivial topological phase. Right, for the emitters, we consider just two-level systems. And these are characterized by a transition frequency, delta, which actually is the frequency difference between the transition and the resonant frequency of the cavities. And the interaction between the two is described by this simple Hamiltonian, which is just the typical electric dipole type of interaction within the rotating wave approximation. And I wanted to say that these alphas here, they can be some AJ or BJ, depending on the sublattice to which the emitter is coupled. So we assume that the emitters are coupled locally to a single site. All right, so this bath has two bands, and because the system has time reversal symmetry and chiral symmetry, it belongs to the BDI class, which in one dimension could support in principle infinitely many different topological phases, right? And these topological phases are characterized by a topological invariant, which is the winding number. So this winding number is a function of the eigenmodes of the waveguide, and it simply corresponds to the winding of this complex phase, which is the same as the winding number of this off-diagonal term of the Hamiltonian. So for the SSH model, actually there are only two different values of the winding number. It could be 0, and then we have, sorry, I don't know why it's jumping. When it's 0, it's a trivial phase, and when it's 1, it is the non-trivial phase, and we have two eigenstates which are exponentially localized on the edges, as you can see here in this picture. All right, so what are the theoretical tools that we have to investigate these systems? One of them is master equations, and these master equations are useful whenever the system is in the Markovian regime. So that is when the dynamics of the excitations in the bath, they are much faster than the typical system dynamics, than the typical dynamics of the emitter, which is the subsystem that we are interested in. And then if that is the case, what one can do is trace out the bath degrees of freedom, and one obtains a master equation for the reduced density matrix of the emitters, which is the one shown here. So let me go term by term, explaining how it is. So the first term accounts for the internal dynamics of the emitters. The second corresponds to effective coherent interactions between the emitters induced by the waveguide or by the photonic structure that you have. And the last one corresponds to dissipation and decoherence induced again by the coupling with this photonic structure. And these parameters, these J and N and gamma, they are related to the correlations in the bath. So in fact, they are the real and imaginary part of the collective self-energies, which are these function that I'm showing you here. So here, these B sub M and Bn, these are the bath operators that couple to the nth or the nth emitter in the interaction picture. Right, and since we have a structured bath with two different sublattices, we have to consider in principle different functions according to the sublattice to which the emitters are coupled. But if one has time reversal symmetry and chiral symmetry and any other symmetry, these will impose some restriction on the self-energies. And in particular, time reversal symmetry makes the self-energies be symmetric with respect to the exchange of the emitters. And sublattice symmetry, what makes is that in reality, it doesn't matter whether you are coupled to the A or to the B sublattice. It only matters if the emitters are coupled to the same or to different sublattices. Okay, so that is one of the tools that we have. But for simple enough systems, we can even go beyond the Markovian regime using the resolvent operator, which is this G of Z, this operator here. And this is nothing but the Fourier transform or the time evolution operator of the system. So if you want to know what is the transition probability amplitude between any two states, one just has to compute the the integral of the corresponding matrix elements of the operator, of the resolvent. So if we are interested in the emitter dynamics, we have to use the projection of this resolvent in the emitter subspace. And it turns out that it depends on this function sigma, which I call them the same as the self-energies I was talking before, because they are nothing but the analytical continuation of those self-energies. So for the Markovian description, we only need to know these functions, these self-energies at the emitter frequency. But if one knew how are these self-energies for any possible value in any complex argument set, then one would be able to compute the dynamics exactly. And this is precisely what we did in our work. We obtained closed formulas for the self-energies of emitters in this SSH model. Okay, so let us start with the simplest case, which is having a single emitter coupled to the SSH model. And I will start discussing the band regime, that is when the emitter frequency is in resonance with one of the bands of the model. Then, according to this Markovian description, one expects to have some exponential decay. The emitter will emit a photon and it will decay to the ground state exponentially with a decay rate that is given by Fermi-Golden's rule. So it is proportional to the density of states of the path. However, if one does this more carefully using this resolvent formalism, one can show that indeed there are other contributions to the dynamics. So of course, this depends on how one integrates this resolvent, this green function. One can split the dynamics in different ways, but the important thing is that there are some contribution coming from branch points of the green function that do not decay exponentially, they decay algebraically. And this is particularly relevant whenever the transition frequency of the emitters is tuned, for example, to one of the band edges. And this, we can understand that in this point, precisely the Markovian assumptions do not hold anymore, because there the group velocity of the modes in your bath is zero, it vanishes. So it's no longer true that they are much faster than the emitter dynamics. All right, but now let us go back to our question. Is there any effect of the topology? And in principle, the answer is no, because, well, this decay rate, this density of states is insensitive to the topology of the bath. You can have a path that is trivial and another one which is topological, and both can have the same density of states, right? And one can even show this in the resolvent formalism, just looking at the single emitter self-energy, and it turns out that it does not depend on the sign of delta, which, remember, according to our parametrization, it was the parameter giving you whether the intra-cell hopping is stronger or weaker, right? Right. So a more interesting situation occurs when one has two emitters coupled to the SSH model. Then, due to the symmetries of the bath, the time reversal symmetry and chiral symmetry, it turns out that the symmetric and anti-symmetric superposition of having an excitation in the first emitter or in the second, these two states coupled to orthogonal bath modes. So this allows us to treat this problem as two independent single emitter problems. And the respective, the corresponding decay rates for the symmetric and anti-symmetric superpositions have this form. So they are equal to the single emitter decay rate plus or minus this collective decay rate. And here in this formula, you can see what is this collective decay rate for the situation in which the emitters are coupled to different sublattices. So here, K of delta would be the momentum of the resonant modes. X12 corresponds to the distance between the two emitters. And this phi, it's the phase of the resonant modes that also enters here in the expression. And as you can see, this expression is bounded. It can be at most plus or minus gamma E, the single emitter decay rate. So these decay rates of the symmetric and antisymmetric superposition could be at most twice the decay rate of a single emitter, but they could also vanish. In fact, these two things are correlated. So whenever either the symmetric or antisymmetric superposition decays twice as fast as a single emitter, then the other linear combination doesn't decay at all. And this is what is known in the literature as subradiance and superradiance. So now remember that what determined the topology in this model is precisely this phase, the phase of the eigenmodes as the momentum goes through the previous zone. So this implies that these super radiant and subradiant conditions depend on the topology. And this is one of the first effects that the topology has on the emitter dynamics. And this has important consequences, for example, in the single photon scattering. So if we now consider this experiment in which one sends a photon of a given frequency and looks at what is the probability that this photon is reflected or transmitted, then these scattering coefficients actually depend on the resultant evaluated at the frequency of the incoming photon. So it is not surprising that, of course, if the self-energies are different, depending on the topology, this will have an impact on the scattering. And this is what is shown here in this picture. So it's very useful to consider this energy level scheme here to understand what is happening. Let us consider a situation, a set of parameters in which for a given positive value of delta, we are in one of these super subradiant conditions. And then what happens is that the photon, the incoming photon, only sees a two-level system. And therefore, the transmission probability shows this single Lorentzian dip with a width that is actually twice that the decay rate of a single emitter. So this is a very well-known phenomenon. Whenever you have a two-level system and you do a single photon scattering, if the frequency of the incoming photon matches the frequency of the emitter, it will be perfectly reflected. And this is what we observe here with this resonance. And then for the same value of the parameters, just simply changing the sign of this dimerization constant, this super subradiant condition is no longer met. And then the photon would see a different energy level structure. And as you can see, the transmission spectrum will be completely different. And this has actually been measured in experiment. For a single emitter, I said that there's in principle no way to distinguish the two topological phases, but this is only true if the emitter is coupled locally. If the emitter is coupled to several sites, one can show that the self-energy of this emitter is actually like the sum of the collective self-energies if one would have like independent emitters coupled to every site. So now this non-local emitter, or which is also known in the literature as giant atom sometimes, it will be sensitive to the topology. And the way it can be seen in single photon scattering is that this configuration, when the emitter is coupled to several sites, to different sites in different sublattices, it will have a lamp shift, a renormalization of the emitter frequency that is dependent on the topology of the bath. So here, for example, the case alpha equal to 0 is when the emitter is coupled just to a single site, and then we observed a single dip that occurs when at 0 tuning. But if the emitter is coupled to, the alpha is different from 0, then this dip shifts away from 0 tuning, and this is precisely giving you what is this lamp shift. Okay, so now I'll go and talk about the other interesting regime, which is the regime in the gap. So what happens if the emitters have a frequency in one of the band gaps of the photonic structure? Then from the Markovian analysis, one would expect that the emitter does not decay, it remains excited. But as Alejandro was explained in his talk yesterday, in reality, what happens is that there is some fractional decay, and a bound state, an atom-photon bound state, will be formed. So these bound states are nothing but the discrete spectrum of the total Hamiltonian. Their energies can be found solving this Dipole equation, and the wave function looks like this. So it has a very high probability that the excitation is in the emitter, but there is some leakage, there is some photonic cloud around the emitter, and this photonic component of the wave function is actually given by the collective self-energies. And the most interesting thing is that the shape of this photonic part actually depends, of course, it depends on the frequency, and is qualitatively different depending on the band gap in which this bound state appears. So in these plots here, in the lower part of the slide, I'm showing you what is this photonic component. So the emitter is coupled to the lattice side in the middle of the plot, in the 0th unit cell. And in blue, you have the probability amplitude in the same sublattice as the emitter is coupled. And in red, it's the probability amplitude in the other sublattice. So all of them, we say that they are chiral in the sense that they are not perfectly symmetric. This is very clear, for example, looking in the example here in the middle of the middle band gap. But in general, they decay exponentially. The ones that appear above the bands are like this one, and the ones that appear below both bands are like this. They are not so interesting because they also appear, for example, if one has a normal 1D chain without any topology. But the one that appears when the frequency of the emitter is tuned to the middle of the band gap is very special. As you can see, it only has weight in one of the two sublattices, and it is completely directional. So it has weight only on one side of the emitter. And we found that the way of this wave function, the way this wave function is actually dictated by the Eigenstates. So having an emitter with this particular frequency is like putting a defect in the chain. It creates an artificial edge, and the photonic component of the wave function will be like the Eigenstate. And this is very well explained in this paper by Leonforte, Carolo, and Ciccarello. Francesco talked about it yesterday, so I won't delve too much into it. But I just wanted to say that we have also considered extensions of the SSH model, for example, considering longer range hopping, still respecting the chiral symmetry. And these longer range hoppings allow for higher values of the topological invariant. And this is interesting because this means that this, first, with higher value of the topological invariant, your chains with open boundary conditions would have a different number of edge states. But now the question is, okay, if you have an emitter and do the same reasoning, that if you tune the frequency of the emitter to the energy of a vacancy mode, then the photonic part of the bound state would be the same as a vacancy mode. What happens here is that, okay, if you put a vacancy, but you still have longer range hoppings, you don't disconnect completely the chain. You don't create exactly an edge, but still one can show that the vacancy mode that emerges in that case is a linear superposition of the edge modes. And yeah, in this case, it still will be perfectly localized in one of the sublattices, but you can, as you can see here in this plot, it can have different decay length on each side and also different periodicity. So yeah, this is, we have also tested how one could distinguish the different topological phases with emitters in this case. And as it turns out, it is very important to have, for example, a non-local coupling to be able to distinguish these different phases. So if you are interested and want to learn more about this work, I encourage you to look at the poster by Carlos Vega. Yeah. All right. So now these bound states, they are very interesting because they give rise to very exotic interactions between the emitters. So remember when I was explaining the Markovian approximation, if you have no density of states, your emitters would not decay, but still the bath can mediate some coherent interactions between them. And these coherent interactions are precisely given by this overlap of the different bound states. So since the bound states, when the quantum emitters are tuned to the middle of the band, of the gap, sorry, are perfectly directional, it happens that for some of, depending on the configuration, and depending on the value of this dimerization parameter, which controls the topology of the bath, the interactions could either vanish completely or be different from zero. And this can be understood very well looking at these schematic drawings here. In one of the cases, for example, for negative values of delta, the two bound states decay towards opposite sides.
The presentation is stuck in the slide of the extended SSH, Miguel.
Sorry?
But the presentation is stuck in the slide of the extended SSH. So I don't know if you have moved beyond that.
Do you see now the different?
It's not moving, the presentation. If you are moving, it's not moving.
And now?
Not yet. Oh, not in my case. I don't know, Anya.
No, I don't see it. So can you, I don't know if it helps to unshare and reshare. I don't know.
Let's do that.
Okay, now?
No.
Maybe I stop sharing.
Yes, let me, now, yeah. Stop the sharing and restart it.
That's right.
All right, you should see now a different.
Now, yes.
Okay.
Yeah.
Right. So I was saying that these bound states give rise to very exotic interactions, and this can be understood looking at their shape. So if for one value of delta, they can decay towards opposite sides, and then these two emitters would not interact. But for opposite values of delta, then these bound states decay towards each other, and there will be a non-zero interaction. And this is what is shown here in this plot. The lines would correspond to the Markovian result, the dots to the interaction given by the resolvent formalism, and in different colors I plot emitters separated by different distances, right? So now, what happens if we have many emitters in this bandgap regime with a frequency in one of the bandgaps? Then they would be described by this effective Hamiltonian with this kind of exchange interaction. And the couplings between the different emitters are given by the bound states. So this is one of the most interesting, let's say, applications of these kind of systems. And it is to be able to use them to simulate exotic spin Hamiltonians. So we went on and analyzed what are the ground state many-body phases that this Hamiltonian gives rise to when we have precisely these perfectly chiral interactions. And we found several different phases. So, well, first of all, let me say that these systems have a great degree of tunability. So, for example, if one moves the frequency emitter towards one of the band edges, then the bound states, the decay length increases. So it is possible to tune the decay length of these interactions by, for example, spectrally tuning the emitters. And then what we found is that if the interaction length is very short, then the ground state is in this valence bond solid phase, which is just like a product state of singlets between neighboring sites. Of course, these interactions pick up the dimerization of the underlying photonic path. And we also have symmetry protected topological phases in this case. In fact, for this configuration, it is rather trivial because for negative values of delta, we just have the two emitters at the ends that are not coupled with the rest of the chain. And when one increases the interaction length, the band gap, we go to a gapless phase, and we dub this phase a double Neal ordered phase. So this can be seen looking at the correlations. So here I plot the spin correlations as a function of distance in the z-axis and the x-axis. And as you can see here in these curves, for large values of the interaction length, we have this double antiferromagnetic ordering that doesn't decay, right? So there is long range ordering in the system. And yeah, this is, I would say this is a very interesting and exciting field because one could in principle simulate many different spin models with the same physical setup. And this is because the bound states differ qualitatively depending on what band gap you place the emitter frequencies. So what I was talking about before in the previous slide is just this situation. But we are now looking at what happens when we consider other frequencies, other band gaps. And we are also considering, let's say, more general kind of
slowly come to an end.
Okay, yeah, I'm finishing right now. So yeah, I just want to say that people have come up with ways to engineer this interaction. So the most natural kind of spin interaction that occurs in the system is this spin exchange, but it is possible to generate, for example, set interactions. And yeah, and well, if you are interested in this topic, stay tuned because we will publish our results very soon in the archive. And with this, I conclude. So thank you very much for your attention.
Thank you very much for this nice talk. Perhaps a quick question. We are also running behind time. I don't see one now, so perhaps you just ask the question.
There is one by Federico Rocat.
Okay.
Maybe you can, yes, above the.
In the chat?
Yes.
Okay. Okay, so I'm reading it, so it's just a bit faster. So is it true in general that the self-energy density of states is independent of the topology, or is it a special feature of the SSH model?
So it's a good question. I think that, so the self-energy, the density of states just depends on the dispersion relation. And I don't think it's just particular for the SSH model, but in general, you can have systems that with close boundary conditions, they have always the same dispersion. And let's say that, for example, this difference between positive and negative values of delta could happen also in other models. So the only thing that determines the single emitter self-energy more than the topology is the dispersion relation.
Okay, thank you. For more questions, just add them to the chat, and then we were going to move on to our next and last speaker of the session. Are you, Eunjung, are you here?
Yes, I'm here. Can you hear me?
Yes, I can hear you. It's great.
Okay, let me share my screen. Can you see the slides?
Yeah, it looks perfect.
Okay, so why don't we get started?
Yes.
So hi everyone. Yeah, I'm Eunjong Kim from Professor Oscar Painter's group at Caltech. Thank you for staying around until the last talk today. Today I'm excited to present our recent experimental result in topological waveguide QED, which is led by myself and my colleague Sherry. Our work is basically an experimental realization of Miguel's work in the previous talk. So for those who are interested in knowing about the details, the talk I'll describe today is now published in PRX, shown on the bottom right. So in the last few years, there has been a trending effort to observe topological effects in various photonic systems, such as silicon photonics, classical RF circuits, to microwaves, to name a few. And this opened the field of topological photonics, and it has enabled unprecedented properties like photon transport without backscattering. So one of the most interesting efforts in this direction is to combine quantum optics with topological photonics, which is the main theme of this conference. And this gives rise to the generation of novel states of light and exotic quantum medibody states. For example, Professor John Simon's group at University of Chicago showed the synthesis of photonic Laflin states, which is a class of fractional quantum Hall state. And they realized using photons in a twisted cavity where the interaction between photons are mediated by Rydberg atoms. Likewise, topological photonics in the quantum regime provides a novel tool for investigating such interesting effects and synthesizing new phases of matter. In that regard, superconducting circuit is an interesting platform where we could engineer photonic structures made of electrical circuit elements. Basically, you can lithographically pattern these circuit elements on chip to make low-loss microwave photonic structure, and you can couple superconducting qubits to the structure to study interesting physics. And there has been many interesting work in this direction. For example, a microwave analog of photonic crystal made of an array of transmission line resonator has been realized in Professor Andrew Haug's lab in Princeton. And they have studied quantum electrodynamics near a photonic band gap, and they have recently even realized a lattice of coplanar waveguide resonators in hyperbolic space. A metamaterial-based approach has been studied in our lab to realize a scalable quantum processor utilizing the qubit-qubit interactions mediated by this engineered photonic structures. Also, it has been shown that using tunable couplers with temporal modulation, we are able to generate an artificial gauge field for interacting photons. And there are still a lot of opportunities at the intersection of quantum optics and topological photonics that await further study in the platform of superconducting circuits. With this motivation, I would like to switch gears to the topological model we have studied in this work. I think Miguel mentioned a little bit about SSH model, but I would like to go through it and define necessary notations here because I'll be using that extensively. So SSH model is one of the most extensively studied topological models to my knowledge, and it was originally introduced to describe the polyacetylene molecule. The model describes this 1D lattice with staggered hopping amplitudes, and it is the simplest model in one dimension with topological properties. So in this model, we have a 1D array of sites with alternating nearest neighbor coupling given by J1 plus delta and J1 minus delta. And this is the unit cell, and each unit cell consists of two sites labeled by A and B. So the intracell coupling is given by J1 plus delta, and the intercell coupling is J1 minus delta. And here the delta is a number characterizing the asymmetry of intercell and intracell coupling, taking the value between -1 and +1. And all the sites are assumed to be at identical frequency of omega naught. If you write down the Hamiltonian in real space, it can be written like this. Here, AN and BN are annihilation operators of sites A and B in the nth unit cell. So due to the discrete translational symmetry, it is more instructive to look at the Hamiltonian in the momentum space. Here, it can be written in this compact form, and AK, BK are now annihilation operators in the momentum space corresponding to A and B sublattice, respectively. And it depends on the kernel of Hamiltonian given by HK, and the off-diagonal term, FK, is the momentum space coupling between the A and B sublattice. Now diagonalizing this Hamiltonian, we can plot this dispersion relation. We can find two bands given by omega plus and omega minus. The annihilation operator of this eigenmodes are superposition of the original uncoupled modes with some phase factor phi. And this is basically a complex argument of the momentum space coupling FK. Now looking at the dispersion relation, we find two passbands and three band gaps. And what turns out is the size of this middle band gap is proportional to the magnitude of delta. And the topological phase transition in this model is accompanied by closing of this middle band gap, shaded in green, as this asymmetry parameter delta is swept from positive to negative values. Therefore, this middle band gap exhibits special properties that will be shown later. So the topology of this model is going to be clear if you plot this coupling term, Fk, in the complex plane. Here, the sign of delta actually makes a difference, while the size of the middle band gap is only dependent on the magnitude of delta. So when delta is positive, when k is swept over the first Brillouin zone from minus pi to pi, this Fk forms a circle inside the complex plane. The important thing to notice is that this contour excludes the origin of the complex plane. So the net change of this angle as it traverses along the first Brillouin zone is 0. On the other hand, for negative values of delta, if we perform similar sweeps of Fk along the first Brillouin zone, what we find is the circle on a complex plane enclosing the origin. And this enclosing of the origin of complex plane is associated with non-trivial topological invariant, which is called the Zach phase. So this Zach phase is a 1D analog of Berry phase. We can actually plug in this definition of eigenmodes in the system to evaluate the Zach phase in both of these cases, and find that the Zach phase is minus half the change in the winding phase, as the quasi-momentum k is swept over the first Brillouin zone. So for positive value of delta, it results in the Zach phase of 0, and the negative delta always gives Zach phase of pi. So from all these math, there are two main takeaways. First, there are two topologically distinct phases depending on the sign of delta. And also there's this phase factor phi, which is a complex argument of the momentum space coupling that is directly related to the topological phase. Now so far we have talked about the topology in an infinite system, but however, it actually has an ambiguity since it completely depends on the choice of the unit cell. For example, choosing the unit cell like this, the intracell coupling and intercell coupling is given by J1 plus delta and J1 minus delta. On the other hand, a different choice of unit cell like this swaps this relative size of inter and intracell coupling. Therefore, there is an inherent ambiguity of topological phase in SSH model when discussing the bulk properties. However, for systems that are finite or in considering a particular section of the bulk, this unit cell can be uniquely defined, and the topological phase can actually mean something. In the remaining part of the talk, I'll use the convention that these circles represent photonic sites, and the distance between circles specifies the coupling between sites in a way that smaller distance corresponds to larger coupling. Now let's briefly talk about the mode spectrum of SSH model in the finite size system. In the trivial phase, we can see that the modes are distributed according to the dispersion relation, falling into two bands of modes. However, in the topological phase, when the intercell coupling is larger than the intracell coupling, or the negative delta, we can consider the edge of the system as an interface between the array in the topological phase and a trivial vacuum. Therefore, topological edge states form at the boundary of the system, and it can be shown that the edge states has exponentially decaying envelope, and the photon occupies only one type of sublattice localized near the boundary of system. So this SSH model is pretty simple and elegant to realize, and there has been very nice work using the Rydberg atoms and superconducting qubits, just to give you a few examples. And in both of the work mentioned here, they use quantum emitters themselves as sites of the SSH model, where photons can occupy, and they have observed phenomena like interaction between edge states. And in the seminal work by Antoine Brawy's lab, they showed the topological robustness of many-body ground state. So the work I have described so far has focused mostly on the states within topological systems themselves and their robustness. However, it is also interesting to think about using those systems as a quantum light matter interface. So in the context of quantum light matter interface, there has been many ideas to use periodic electromagnetic structures to induce photonic bound states with quantum emitter. Specifically, coupling a quantum emitter to a periodic photonic structure at the bandgap frequency, the emitter hybridizes with the modes inside a transmission band to form qubit photon bound state, which has photonic tails exponentially localized with respect to the position of the emitter. Basically, you want to utilize this photonic structure as a medium for imprinting interactions between emitters and use those novel interaction connectivity to study quantum antibody models. It has been discussed that photonic bath with topological properties indeed introduce novel properties to a collection of quantum emitters. For example, utilizing a bath with chiral character, it has been shown that you are able to create a cascaded quantum system with unidirectional feedback, allowing one to create pure and highly entangled state under driven dissipative methods. Also, utilizing a topological photonic bath with directional character, which is the focus of our paper, you are able to create a novel quantum order called the double Neal state, which I'll be describing in the later part of the talk. So employing topological photonic bath provides new opportunities to generate and study exotic classes of quantum entanglement, taking an angle different from conventional topological photonics approaches. And we have constructed this SSH model with linear resonator array. And by coupling superconducting qubits to this array, we study the properties of qubits endowed by the topological bath. With this motivation, we have realized this canonical SSH model with superconducting electrical circuits. So the unit cell of the designed array consists of two LC resonators with alternating capacitance and mutual inductance. The metamaterial realizing the circuit is illustrated on the right, which shows an optical micrograph of a unit cell of the device. Here, the red and blue are LC resonators whose coupling strength between them, including the capacitive and inductive contributions, is controlled by the distance between neighboring resonators given by TV and TW shown here. We have fabricated the test structures in the trivial phase and the topological phase by controlling this inter and intracell distances and measured the transmission spectrum. So the peaks in transmission spectrum signifies the presence of a mode at that frequency. And we find the emergence of a mode inside the middle band gap in the topological phase and absence in the trivial phase, telling about the presence of edge states in our system. Now things get more interesting if we couple qubits to this metamaterial waveguide. Here we introduce this device where we have performed interesting spectroscopic experiments with using qubits. So the device consists of 9 unit cells in the trivial phase, meaning then the intracell coupling is larger than the intercell coupling. And we have coupled superconducting transbond qubits to every site on the 7 inner unit cells. So there are in total of 14 qubits in this device. And each qubit is connected to a flux bias line, allowing for individual qubit frequency control. The qubits here are labeled by their unit cell index as a subscript and the sublattice index as a superscript, as shown here. So Q1A means qubit coupled to the A sublattice of the first unit cell. To effectively access the topological waveguide through spectroscopy, we have added tapering sections at the boundary, which performs impedance matching to the external waveguide ports, which are denoted as P1 and P2. The tapering section in this specific experiment was designed to reduce the ripples in the upper transmission band, allowing us to mimic the system in the thermodynamic limit at passband frequencies by reducing the amount of reflection at the system boundary. And this enabled the passband experiment, which will be discussed later. So we have seen earlier that coupling qubits to a bandgap induces a photonic envelope surrounding the qubit. And surprisingly, it has been shown that in the case of SSH photonic bath, a completely directional bound state can be realized when the qubit transition frequency is resonant to the reference frequency omega naught inside a middle bandgap of the SSH model. What turns out is when the array is in trivial phase, coupling qubits to sublattice A, the qubit photon bound state has photonic envelope directed to the right with photon occupation on every B sites, which resembles the left edge states in the topological phase. This surprising directionality can be proved by using the coupling of tail of the bound state of the external ports in a finite size system. So coupling qubits to a sublattice B, it actually opposite to qubit A, it's coupled to site A, it induces photonic bound state directed to the left. And these external decay rates, kappa E1 and kappa E2 of qubit photon bound states to external ports P1 and P2 allow us to probe them. And to find the dependence of directionality with respect to the frequency, we perform spectroscopic measurements on Q4b, which is located near the center of the array on sublattice B across the middle bandgap frequencies. So measuring the reflection spectrum from port 1 on the left, what we find is a dependence of the external line width on frequency as a function of frequency shown on the left. And at all frequencies, we measure appreciable external line width as shown here. On the other hand, measuring the reflection spectrum from the opposite port, port 2, we see that the external line width completely vanishes around 6.6 to 1 gigahertz, and we are not able to find the same qubit photon bound state. And this is one evidence that this directional bound state only is coupled to the port, single port, due to this weird shape. To further characterize the shape of the qubit photon bound state, we have measured the external line width of all 14 qubits at the most directional frequency we found, and the external line width from port 1 and port 2 as a function of all the qubits at the middle frequency, this reference frequency, shows this directionality of qubit photon bound state, as well as the alternating photon occupation distribution that resembles topological edge modes. So the consequence of directional qubit photon bound state is this direction-dependent photon-mediated interaction between qubits. And to show this, we have considered two examples of qubit pair in which bound states are facing toward each other and when they are facing away from each other. In the former case, we have measured the avoided level crossing centered at the reference frequency and find the splitting to be around 65.7 megahertz, indicating a very strong interaction. On the other hand, for a pair that is facing away from each other, we don't see the levels avoiding each other, indicating the absence of interaction, although the actual distance between qubits in this case and this case were nearly identical. It is only through a more careful measurement we find the level splitting to be smaller than a megahertz. So we have performed similar crossing experiments between various combinations of qubit pairs in our system. And the plot shows coupling between qubit pairs where the first qubit is on sublattice A and the other qubit is on sublattice B, plotted against the cell displacement. And what we find is a clear direction-dependent coupling that decays exponentially with the displacement in one direction, while in the other direction, the coupling is vanishingly small. We note that this directional interaction profile depends only on the relative displacement between qubits, not on the actual location inside the system. And from the exponential fit to the data, we have found localization length of 1.7 in units of units of lattice constant, which realizes an intermediate range photon-mediated interaction. Note that this complete directionality is present only at the middle of the middle band gap when the bare qubit frequency is resonant to the bare resonator frequency. And in other band gaps or other frequencies, other frequencies of the middle band gap, this complete directionality is broken. So far, we have looked at the band gap regime, especially the middle band gap of the topological waveguide, and tuning qubits resonant to the photonic band. I will show that we can actually use qubits to extract the topological phase of the waveguide. So plotting the dispersion relation of an infinitely large topological waveguide, we observe no difference between trivial phase and topological phase because the size of the gap is proportional to the magnitude of delta. And as mentioned in the introduction, the topology of the band in the Ssh model is encoded in the phase of winding, which is a complex argument of this momentum space coupling Fk. And we have also seen that plotting Fk on the complex plane as the quasi-momentum k is swept across the first Brillouin zone. The enclosing or exclusion of this contour on the origin actually shows the phase, topological phase of this waveguide. So in the trivial phase, where delta is positive, the circle excludes the origin, and in the opposite case, delta is negative, it encloses the origin, and it's the topological phase. And it will be very interesting to be able to experimentally measure this quantity, which will tell us about the information about the topology. And how would we achieve this? As Miguel mentioned, the idea is to utilize the waveguide QED tool and look at the cooperative interaction between pair of qubits. So if we consider a simplest scenario where two qubits are placed along a regular waveguide with linear dispersion at a distance of delta x, there are two processes happening. One is the coherent exchange interaction, JC, and the other is correlated to K gamma C. And the rate of these processes are shown to be proportional to the sine and cosine of the phase length delta phi, which is basically the phase accumulated by when a resonant photon travels across the waveguide along this distance. And due to this effect, when delta phi is equal to the multiple of pi, what we see is the perfect bright and dark states, also known as superradiance or subradiance. So what turns out is in the case of topological waveguide, this phase delta phi, which determines the coherent interaction JC and the correlated to K gamma C, is modified to contain the phase of winding, which this phase, the argument of the momentum space coupling between A and B sublattice. And this means the super and subradiance of two qubits coupled to the topological waveguide will contain information about the topological phase. Yeah, I think I'm running out of time, so I'll briefly mention. So how we can see this is that if we consider the cell distance of 2 when one qubit is coupled to A sublattice and the other qubit is coupled to B sublattice, what we find in the trivial case is inside the passband frequency, there is only one frequency point where the coherent interaction vanishes. crosses the 0 point. On the other hand, in the case of topological phase, we find two such points where this JC vanishes, and that's basically when the perfect superradiance occurs. So what we can do is we can resonantly tune a pair of qubits across the upper passband, and we can count the number of frequencies where we observe this perfect superradiance. And here's our experimental result. We have measured transmission spectrum across the upper passband as two qubits separated by 2 unit cells are resonantly tuned. So in the trivial phase, we found a single point in the upper passband where we observed this weird swirl patterns as indicated by the arrows. And this pattern arises from the disappearance of peak in transmission associated with the interference between photons scattered by imperfect super and subradiant states. And the center of this swirl pattern is where the line width is maximized, corresponding to a point where the perfect superradiance occurs. In the topological phase at the same cell distance, we observe two such points with swirl patterns, indicating the number of superradiant points is 2 in the case of topological phase. And we find a pretty good qualitative agreement between the theory and the experiment. We have performed similar resonant tuning experiments for various qubit pairs with a variety of distance, and we were able to show that this number of swirl patterns across the upper passband differs by exactly 1 between the trivial phase and the topological phase. And our data shows good agreement with the theory. And therefore, we have shown that utilizing the waveguide mediated interaction between qubits, we can really probe the topology of the photonic bath it couples to. So this will be the end of the main results of our work. To summarize, we have created a light matter interface using topological photonic bath, and we have observed interesting effects associated with qubits inside the middle bandgap and in the passband. Also, although it's not discussed today, we have in the paper, we have also demonstrated quantum control over topological edge states using superconducting qubits. Looking forward, the characterizations done in this work lays the groundwork for a few different interesting directions. First, the directional coupling here, as Miguel mentioned, gives rise to a very weird interaction profile. And if there are multiple qubits coupled to the structure, the long-range interaction together with the directionality can actually induce exotic many-body state called a double Neal order, where spins are anti-aligned with a period of 2 sides. And along with the utilization of topological edge modes, we can utilize top tunable coupler, which are pretty common in superconducting qubit community. And this will allow to control the localization length in situ. And we can actually build very long waveguide to realize a robust quantum state transfer. And we can also study other kinds of dressed states, vacancy like dressed states, using a different kind of topological waveguide. So before ending my talk, I would like to acknowledge funding from these agencies, and I would also like to thank our lab members at Caltech and theory collaborators at CSIC. And I'll be happy to answer questions.
Great, thank you. What nice results. That's really great. And we have, I see already one raised hand from Francesco.
Mm-hmm.
You can, I think.
Can you hear me?
Yeah.
Yes, I can hear you.
Oh, hi. Thanks for the nice talk. I had 3 curiosities regarding things you can implement in the future.
Yeah.
One, whether you can implement complex couplings, because there are a lot of topological models which need complex couplings. 2, whether you can implement next to nearest couplings. And 3,
next nearest neighbor coupling.
Going beyond nearest neighbor couplings.
Okay.
And 3, whether, how long we are from having a 2-dimensional photonic lattice.
Okay, those are very good questions. So I guess what you mean by complex coupling is something that breaks the time reversal symmetry, Am I correct?
Yes.
Yeah. So as I mentioned in the introduction, there's actually, like, if you are able to incorporate tunable couplers, and if you could perform, modulation of those coupling in time, you can actually introduce complex coupling that way, breaking time reversal symmetry. It's like, adding artificial gauge field to the system. So it's definitely possible. And also related to your second question on the next nearest neighbor coupling, I think in reality, the system has, it's a real system, and the system has some sort of next nearest neighbor coupling. I guess if you mean next nearest neighbor coupling between resonators in an array, I think it's already present.
I guess so, but the question is whether you have control on that.
To have control on that is a different question. I guess there's nothing fundamentally impossible, but you just need to, from a circuit engineer's point of view, you need to engineer things properly such that these couplings are exactly something, right? I don't see a reason why we cannot engineer those, but of course there's some, to some extent, I think could be some limitation which I might not have thought in detail. And also your last question on 2D.
The most challenging.
Yeah, 2D is also possible. Yeah, I'm saying it's always possible, but of course, I can tell you about the challenges in going to 2D in our platform. So basically, as you can see already here, we are laying out all these features in 2D. And the great thing about superconducting circuit system is that you can add these individual wires to control them in situ, which comes from the perimeter of the chip, right? And if you look at leading superconducting qubit work like Google did, it's actually possible to approach from third dimension by doing some smart engineering. But this is something that we don't have yet. But if we have those tools, it's what I mean is it should be possible. There are people who are able to do these clever wiring going in the third dimension from the chip. So yeah, it should be definitely possible.
Okay, thank you.
Okay.
Great. So I don't see further question. Perhaps I can ask a really simple, and perhaps I have missed it, a naive question. So if you like do your experiment, you excite the qubits from the outside, and then you look at the output of the waveguides, correct?
Yes, we excite from the waveguide port, and we prove them by utilizing the coupling of this qubit photon bound state to these external ports due to this extended photonic envelope.
So, but you're like, because the picture you have is always this, that you go to the right? The chiral aspect, but you're exciting it through the waveguide.
Yes, we can excite through either left or right. So we can probe the coupling to the left port or to the right port simultaneously.
But is this then in the end a reciprocal situation because you can go back out and in like a?
Yes, this is completely reciprocal situation. We are not breaking time reversal symmetry here.
Okay, great. I don't see further questions. It's also, we are like a little bit over time. I thank you very much for this great talk. It was a perfect finish for this great day. And I'd like to thank everybody for being here today. And I hope we all learned something, and we will see you all tomorrow.